And let's get the slideshow set up from current slide. But before we get going on that, we have a couple of options. Wish more people were here. Kind of killing time till I think it's Tyra comes back, but I need to go and get it done, I guess. I did finally, I called several times Thursday, emailed, hadn't gotten a response, but I called Friday and was able to get in touch with Mr. Weigel at Sanford, and he said Thursday would be a good day. He said the earlier time rather than the later time, so let's plan right now to go to Sanford University. I figure that some people, if they have a class right before this one, they probably can't, boy, whatever I did, it must have been all right. They start flying in now. Okay, James is here, and Shelby's here. And Tyler. Okay. It's not like it's good. I had seen you, thought I caught a glance of you, but then you weren't here, and I thought, was that Tyler? Okay, I didn't want to mark if you weren't. Okay, we're still missing then Darius, Josh, Carl, and Tanisha, and Terry. Okay. I wish more were here. But I talked with him, and he said Thursday would be a good day for the lab. Okay? All right. Tanisha? Yeah. I had something for work study to do, but I thought he had already left, so I went on and did it. I wish I hadn't, so I got it. I was going to have you call the library, but I called him because I thought you were already gone. Okay. Okay. We are going to Sanford on Thursday, and is that going to give you time to make arrangements?
Yeah, my class.
Yeah, so therefore we won't leave campus here until 12:30. And I told them not to expect us before 1:15, but I said I couldn't guarantee we'll get there at 1:15, but I think we can get pretty close to that. Okay? Now, I don't have the van reserved yet. I'm going to try to get that done. If I can this afternoon after class, but I have a feeling everybody will be gone by then, so it'll probably be tomorrow afternoon before I'll be able to reserve the van. But you're going to have to handle your own transportation, right?
I got it.
Okay.
Needed to know what time.
That's what?
I just needed to know what time.
Yeah. Okay. So I figure if we leave here at 12:30, which, judging by what time people came in today, that may not be I've got to leave here at 12:30 to be there at 1:15. So if you can't be here by 12:30, plan to get there however you can. But we'll be starting there at 1:15. He said he'll go probably between 1 and 2 hours, okay? So I want to make sure everybody that can hears this. We will be going to Sanford on Thursday, okay? And he's going to shoot for us getting there about 1:15, which means we've got to leave here at 12:30, not at 12:50, okay? So we've got to get it. If you're going to ride in the van, which I don't have reserved yet, then the van is leaving at 12:30. Understood? And if you're driving yourself, just get there by 1:15. Okay. Now, are all of you somewhat familiar with Sanford's campus? If you are driving yourself. You know when you go to Sanford's campus, it's on Lakeshore. And there's a couple of different entrances, maybe even 3. But the main entrance has lights there, a big gate. You go in one way, come out another. The gate's in between. Okay? You know what I'm talking about. Okay? It's in between I-65 and Brookwood Mall, right? Is that right? Yeah, that's on the right side. I'm trying to picture it myself. Okay? So, closer to Brookwood Mall. So I think it's a little closer. So anyway, that's where it is. You turn in at that big gate. When you turn in, I don't remember the name of that road, but the very first crossroad to that, there used to be a stop sign there. I think they took the stop sign down. Last time I gave directions of stop at the stop sign, then I found out they took it down. So the first crossroad there is, map somewhere here. Oh, the stats are too deep. Here they are. Here it is. Well, yeah, here it is. Now, if you need me to make you copies of this, I certainly can. This is a map of their campus. Okay. I don't know if you probably can't see from where you are. This is Lakeshore Drive, Brookwood Mall's this way, I-65's that way. There is an entrance over here, it's called Montague Alley. I wouldn't suggest going in that. I'd say go on up Lakeshore until you hit the light, the big double gate. You see the entrance here, exit there, gate in between, big fancy, nice gate there. Looking up the hill, you see the library here. It's a really typical entrance to a college campus, big building on top of the hill. Okay, so what you do, you turn in that road, the entrance here, at that first cross street is Montague Drive. Montague Drive pretty much circles most of the old campus, a lot of the new campus too. So you get on Montague Drive, take a right at that first place that you can, take a right, and be sure you keep veering to the left, okay? Don't get off on Garreau Hodges Drive. You don't want to go down there, that's faculty housing or something. You don't want to go there. Keep on Montague Drive. It makes a gradual left-hand turn until you're going 90 degrees from where you were going, basically the same direction you were when you came in. There are a couple of stop signs here. Right up here is a conservatory, and at that entrance is a stop sign. It's a pedestrian crossing, is all it is. The second of those stop signs is up here right at the planetarium, okay? That's the second of the cross signs. However, if you're driving, you can't park right there. And for you, I'm pretty sure, and for anyone, can try to park in that first little parking lot past the planetarium. It's not obvious the planetarium's there. If you look very carefully, you'll see a little sign, but it's not obvious. But that second stop, that walkway there, the planetarium's off to your right, okay? Just past that is a parking lot down there. Not a very big lot, and quite often by 1:15 in the day, it's probably going to be pretty close to full, but that's where your ride will drop you off because the entrance is somewhere off of that parking lot. Now, I can't tell you exactly where, but I think it'll be fairly obvious to you. I just never have looked for it, so I don't know exactly where, but you'll enter the building from the parking area down there. Okay, the rest of you, if there's no parking here, then go on up to the top of the hill. It's called the Northeast Parking Deck, okay? There is a little lot, that's open lot to the right. If there's any places there, you can park there, or get in the deck. And the deck is 2 levels, the one you enter and then one that you go up a level, okay? Usually, every time we've been there, enough people have found parking in that deck. Occasionally, we'll find parking in that first little lot there to the right, so look. But if there's not enough spaces, go on up to the main parking deck, either the lot to the right of that or the parking deck that is a 2-level deck. Okay, now I'm not absolutely certain, but I think if you turn in the front side, the first entrance to that, you only get to the lower level. I think you have to drive a little further down to get to the upper level. I think there's no way to get from level 1 to level 2. You either come in this way for the second level, this way for the first level, okay? The hill is shaped that way. So most people can park there. I in the van, if I can, we're going to park down here. If not, I'll let you off in front of the planetarium unless you just want to walk down the hill, and I'll be parking up there somewhere, okay? And we can either walk together or you can walk. Now, if I get there early-ish, which I hope to, then I will be out here at that second stop sign and, you know, visible so you can give you directions of where to go from there. If we don't get there early, then there won't be much time for me to be there. But that's why I need to leave here right at 12:30, so I can try to be there a little bit on the early side. But I can't judge traffic or anything else. Now, are any of you wanting to drive and follow the van? If so, you have to be here at 12:32 because the van is leaving at 12:30. But if you know how to get there and stuff, now since we're leaving here at 12:30, getting there at 1:15, finishing there, say, I'm just going to guess 2:30-ish, then we got plenty of time to get back to campus and complete class, okay? We'll have our lab first and then class afterwards. In fact, we're going to finish chapter 17 today. We're going to do the lab for 17 today, which means we will have time for the test on Thursday after we get back, okay? So if that's inconvenient, and it may be for your driver and stuff, I don't know, this is probably your last class of the day, isn't it?
I'll figure it out.
Okay, but if you need to go back, you can and pick up the test later, yeah, whatever.
I'll figure it.
Okay, but the rest of you too, if some of you say, well, I want to go home after that, we will be having the test after we're here. I'm here till 5 o'clock, so we will have the, we may actually have some class in chapter 18, but we definitely have the test in 17, the last 30 minutes. So if you can get back here, I suggest you do so. Now, I understand if you live right over there near Sanford and you want to drive back and forth and stuff, I understand, that's your choice, but you will need to make it up then, okay? Any questions on the field trip? Yeah?
You said after you come back.
Yeah, we'll be through there by probably 2:30, and the class goes until 5. So we've got a good hour and a half left, 45 minutes back. We will have time for the class, at least the test afterwards. And a lot of you need to come back anyway. I'd rather bring the van back, so everybody in the van will have to come back here anyway. So we will be, but if that's inconvenient, you can make up the test later, okay? But you'll just have to do that during my office hours or after class one day or before class one day. I've got office hours before class and some a little bit after class, so don't sweat that. Okay. Any question on the lab? We will be going to Sanford then. Now, the other part, and I've basically just about used all the time, I was going to give you the option that we could continue chapter 17. We might even be able to finish 17 before we do the lab for 17. But it's already 1 o'clock, and technically we're supposed to be out of here. Well, we don't have to be out of this room before 4, but some of the students start coming earlier. So we can either finish the chapter and then do the lab, and then move to the other room and start on chapter 18, or we can do the lab now and then continue chapter 17, finish the chapter, move and go to 18. I mean, we can do it either way you want. You want to go on and start the lab, or you want to, you do? Okay. I just thought if you wanted a break in between so you don't have to listen to me talk so long in a row, that's going to be an option. But you've chosen now, so you stuck with it. Okay. Just kidding. Okay. Sort of. Here's the lab. And the reason we're doing the lab first today is because we have access to computers here. This is the one, probably only, computer lab we'll have in this class. Okay? I did want you to have the opportunity to do that. Now, the students who were here said that access was, if you can't get on your computer, try typing access. I'm going to turn this off to save the, I thought it was kind of that. You don't do this. Now, you'll need a computer screen. Did you get one? Yeah. would suggest a pencil. I just saw someone get out a pencil. You all got a pen, that's fine with me. But I would suggest a pencil, just knowing how this is going in previous terms. Oh, wait. God! No, I started screen casting at it. I was afraid I did all that talking and didn't get it on the thing, but we're here. So get there on computer screen. If you want to work with a friend, this is a lab, so you can work in pairs or buddy, or you can look yourself, okay? So do however you want. I see most people getting your own computer, perfectly fine to do so, okay? Okay. Okay. Now, do I have sort of everybody's attention, at least for now, before you get going on the way? Yeah. Okay, my hearing's bad. ACCESS. Not kidding me. Huh? Did everybody get on with access? Okay, some of you got on with access, all right? ACCESS. That was it. Any caps? No caps? Okay. I don't know. You can work with somebody else, though. You don't have to be it by yourself. Yeah. So we can't get enough computers. That maybe some of the computers are fried or someone changed something they shouldn't have. Okay. All right. Now, what the lab is, if you recall from earlier in the chapter, and I tried to emphasize it when we were talking about physical properties of common minerals. Now, has everybody in here got a copy of the lab? Okay, good. That's the title of it, Properties of Common Minerals. There's some verbiage at the beginning, well worth the read, and it talks about developing a table of mineral properties. Okay? Now, what they're saying, pick up the mineral and mess around with it. Guess what, team? We don't have the minerals. We can't do that. So what we're going to do is go and do it as a computer lab. Okay? So what you'll do, and here is a starting point. You're not going to be able to do the whole lab from this place, but this is a starting point. Go to a site called webmineral.com. Okay? I'll type that out write it out for you. Okay? Now, a few things may have changed, so I don't know if this is absolutely true anymore, but let me... Okay. Okay. Here's the site that I found that works the best. Yeah. What's that? Yeah. Yes. It's not working. Okay. Most people got it to work. Has anyone found any other thing that would work? Yours won't come on, right? Okay. What's that? I can't hear you.
I'm going to get my laptop.
Oh, okay. Or you can use one of the others. Okay. Once you got a computer that's working, here's what to look for. HTTP. Now, that's what it used to be. It could be it's a PS now. S just means secure. Okay? //webmineral, WEBMINERAL. Without an S. There's another site with an S. Leave off the S. Webmineral.com. Okay? If you'll follow that with a /data, now some of these things may have changed. If you'll notice, the first mineral on your list is calcite. So if you wanted to start right where you need to start, do another slash, and then type in calcite. And you can do that for every mineral. You know, go back and just change the header to be slash and then the mineral you're looking for. CI calcite. Okay? And then you go on from there. Okay? If there's more options, you're looking for physical properties. Okay? But once you get on the website, then you'll see tons of information. You'll see pictures of it, you'll see descriptions, you'll see all sorts of stuff. Scroll down, keep scrolling down until you get to the part that says the properties. And usually one of the first ones listed is color. Now under color, and we talked about this in class, a given mineral can have literally dozens of different colors. So write a few of the more prominent ones, okay? You don't have to write them all unless you just want to write them all, okay? Luster usually is going to be 1 or 2 words, okay? Streak is usually 1 or 2 words, okay? Then you flip on over to the next page. Okay, don't go down that page, because if you go across to the next page, you're still talking about calcite. So while you got calcite up there, then you can do hardness, okay? And that's somewhere right in there. And then you'll see, and on your list, it probably lists both cleavage and fracture separately. On here, you want to do them together. So I would do cleavage / fracture just like the head does. Cleavage / fracture. So if it says anything about cleavage, write in a few words. / fracture. Write in a few words. Now, if your particular mineral has no cleavage, then you can leave that part blank. But if it's going to have one or the other, most of the time it will have both. Now, let me warn you about this one. Cleavage, it usually is going to talk about planes. And it'll have a series of numbers, 0101, okay, or something like that. That means that's your cleavage plane. You can list that, okay? Again, you don't have to write everything that's there, but write enough to let me know you knew you were doing what you're supposed to do. Yes? Okay, that was my next statement. The last column here says other. Well, one of the most important, I typed it on my screen, but I didn't turn on my projector. Okay. The other column here, one of the most important properties of a mineral is its density. So other will be density. Or you can put density / specific gravity. Does anyone remember what the difference between density and specific gravity is? Density will usually have units, grams per cubic centimeter. Specific gravity has no units. Same number without units. So either one of them is fine. If it has units, that's density. If it doesn't have units, it's specific gravity. Specific gravity is comparing that density to the density of water. Density of water is 1 gram per cubic centimeter, so you usually lose the units. Now, before you get going too much on this, what I've just shown you, http://webmineral.com/data/calcite. Has anyone found that yet? Right up here. http://webmineral.com/data/calcite. That gets you to the first one. Once you get there, you probably have to scroll down until you start finding the physical properties, right? Now, here's the deal, folks. I can't remember. I think there's something like 18 or so of items here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 19. 19 minerals are listed here. You're going to be able to find, I'm making a guess here, between 15 and 18 of those on this site, webmineral.com. Okay? Some of them you're not going to find on that site. For those you can't find, and I'm guessing right now, it's been a while since I did this, it seems like maybe bauxite perhaps, was one that is not listed there. Bauxite is actually an ore. It will contain multiple minerals. So what I suggest you do, and it won't be just limonite may be, feldspar may be, hornblende I think will be, but a few on here you will not find on this site. Okay? So what you do then, or what I would suggest, is Google those. Now once you Google them, you'll probably find, or use any other search engine you want. Once you do that, you'll probably find that there's a description of it, and it's a class of minerals, not a specific mineral. You pick, if it is that, and I'm pretty sure that feldspar is like that. There are potassium feldspars, there's calcium feldspars, there's sodium feldspars, there's just all sorts of feldspars. So you probably won't find feldspar, but if you look under feldspar, Google that or something, you'll find a whole list of minerals. While you got that, look and see if you can find those minerals in the website. Okay? And if you do, pick the one and write that above feldspar, or if that's it. I don't know if it's feldspar. If you can't find the one that's listed here, Google, see if you can find it. Now, you might be able to find another site that has all these classifications for that mineral. Fine, use it. If not, find a mineral that's related to the one that's listed here. And I'm pretty sure bauxite is one, because that's an ore. It's not really a mineral, I don't think. I think that's the one. So on that one, you'll need to find one of the minerals that's in the ore bauxite, and then see if you can find that either on this website or some other website. Is that enough confusion for you to get going? Okay. Okay. So get going. If you have questions, I'm up here. Ask me. I'll try to answer. Okay? Yes. You what? Okay. Are you on that website? Okay, yes. But yeah, you are. But you see, you stopped the alphabetic. If you go on like it shows up here. Okay, you see, yeah. Okay, yeah. Okay, David Kelso. There it is. It goes right to the same place. Okay, scroll down. Scroll down. You got the bottom? Okay, let's go back up here.
I just looked at it, I was like, I'm doing this ain't smart.
Property.
Yeah, it's
a property.
It's a partial outside.
Okay. Search minerals. Try calcite. Okay. Then try okay. Yeah. Try properties again. Physical properties. So, that's the bottom. Okay, try again. One of the others, like magnetite.
Alright, next class is right there on the top.
Yes, sir. Okay. I'll see if I can get her going. It's going to be nothing. Oh, yeah, it comes.
No. That's what he wants.
Is anyone not having success on this? Okay, is anyone having trouble finding the stuff here, or y'all getting it? Go to one of them and see what they did to get to it. Okay. What's that?
A to Z index. Click A to Z at the top.
Yeah.
And then click whatever the first letter of the word you're looking up is, and then go to that word.
Okay, back up then, go back.
We're just gonna search.
Oh, yeah, there it is. A to Z. Do that. Second? I'm sorry. Search. Yeah, well, we tried that and it wasn't giving her any of that. Okay,
That's what I'm doing is
A
search.
to Z.
If you put the slash data and then slash word, the index will pop up.
Scroll down to see. I see. You clicked on the C index, or did you type it in? Okay, good. No, for my-
But it has a picture. Oh, wow.
Okay.
Colors.
I don't know. How are you doing on it? Please practice. Okay, yeah. Do you have it up now? Okay. Why don't you come look at his and see how we got there? Yeah. Okay. This doesn't, oh, there's the cleavage, I would put those and then slash and then put row. So,
That's it. We're all the same.
no, once is fine. Okay. Yeah, that's what I would do. You see cleavage? Yeah, and then you see that's just the key. I didn't realize same thing 3 times, so just write that once, slash, fracture row. Okay, how did you get there? You were able to do so. Let me see, get to the next one. Oh, okay, you were right before you type. Okay,
Now, yeah.
go back to your A to C.
Oh, what was this street?
Oh, look at you. Okay, wait. Is this the top? Yeah, scroll down some. Scroll down. Scroll down. Physical properties of calcite. There's your coloring, there's cleavage, you put the first one there and then slash, fractal drill. Yeah, you go like that. Go across the page, both pages, yeah, you got it. Okay. Everybody got it going now? Other is density. And that should be your other is density. Okay. Can I turn off the projector just to save on the screen? I mean the bulb? Anyone need the site anymore? You got it? Okay. Now, any other questions while you're rolling along here? Okay. What I'm going to do is go to the lab and get you some samples that you can look at in your viewing pleasure. I'll be right back.
Well, look at this one. Black, gray, or silver gray. What was and the next one is color brown, colored brown. Luster is colored white. And the street is white.
Now, I know most of you are probably already through with calcite, but here, and I think I told you last time, I had in my class one time, this was several years ago now, one of my students actually worked in a coal mine. He said, oh yeah, calcite, we run into that all the time. This is coal on the edge of these, and these are calcite crystals that you see, and you can see beautifully identified crystal planes, cleavage planes on these. We'll get your hands a little dirty, but if you want to look at this and pass it around, those are calcite crystals. Clearish, whitish, not the black stuff on top. And for those interested in a little bit closer look, these are some smaller crystals that broke off those. You broke one. Calcium carbonate, that's coal, and that's pure carbon, this is calcium carbonate down here. So it looks all like carbon, this is it. Yes. Right. Private work, so when you have a whole bunch of listings, just click any one of them. Yeah, it was all amazing crystals. Large crystals. What does large crystals mean? Large crystals indicate? Slow, yeah, slow formation. The crystals form very, very slowly. Yesterday, he was talking about the crystals, the large crystals they do in space. They form very, very slowly. Yeah. Well, that's one of the few pure. What's that?
The fine ones, that's the one with heat.
Say this again.
Fine crystals is when there is heat applied.
Say this again one more
The
time.
fine crystals.
Yeah. They were formed very quickly.
Very
Yeah, yeah. The large crystals form slowly, small crystals form rapidly. Set this all up on the table here, and now I probably need the table. That's the only thing I can roll around and show. So,
Yeah, that's right.
what's that?
I'll have to read another one.
What's the
I think that most of the crystals you see here are probably quartz crystals. You saw the hexagonal shape in the text. These are actually stones that probably are mostly quartz crystals. That they call pink quartz. That means there's traces of some impurity on it to give it a pink color. So you see, it's hard to judge quartz by the color because it can be just about any color. Always light colored, of course. But this is pink, that's white, but it's probably the same mineral. I think these are both samples of quartz. Large crystal size, yeah. You can see some of those hexagonal prisms. Yeah.
Part of this is 2.5. And this is perfect. And
Is there another word for cleavage or fracture?
Second.
Is there another word for cleavage or fracture?
No, is this a different site or the same one? It is the same one. And which mineral is this you're looking at? Chrysotile? Okay. Yeah.
yeah,
Sure don't see it on there. Let's see. Does it have any description at the beginning? Okay, scroll up, scroll down, and see. Keep going. Okay, now there's a whole bunch of things there. Okay, go on down to this one, see what else it says. Other information. So,
yeah, one day.
how much further you, let's just go through one and see what you get. Right, okay, scroll back up. Okay, wait, what's this right in here? No. Okay, scroll back up. All right, right there. Click on one of those and see what you get. Right down. There, it says Chrysotile, one of those. Scroll back, go back. Okay, see what it tells you. Ah, there's a cleavage.
Yeah.
See, that's one of the types of chrysotile. Again, chrysotile probably has a whole, it's distinct cleavage and what's it called? Concordial? Or, concordial. Fraction,
Concordial.
so the cleavage and the fraction. Now some, for instance, Brittany found chrysotile could not find cleavage fracture, so she went to one of the specific chrysotils. Somewhere further down, you saw a whole listing of them, sort of like you found the one that y'all were asking about. And clicked on that, and she found the cleavage and fracture there. So you might need to do that, and when you do, just put in parentheses which chrysotile you're talking about.
Okay, now I have a question.
Okay? I
So,
have no answers.
I have,
Right.
I haven't, let me just look at this. So, I don't see fracture, but I think
There's
it's in cleavage
yeah.
instead.
Yeah, if
So
you can't
that's-
find the cluster, that's fine, yeah.
Okay, so it's,
Yeah, and if you could put something on either one of them, that'll be fine.
okay.
Pardon me? Oh. Yeah, it does. And what you found, I think, about it, let's see, was that one of the things here? Hardness, what was the hardness? It's not that hard. You can almost scratch it with a fingernail, not quite, close. Huh? Okay. Oh, I thought you were complaining it was breaking up on it. Okay.
What kind of egg? Oh,
What's that?
what kind of egg is it?
Dinosaur egg.
Oh, I thought it was an egg. I said, what kind of egg is this? And then I looked at it and was like, oh, it's a lot. Wow. So this is like the outer yolk.
What's that?
What? I don't understand.
Yeah, it's called the, goodness, I just had the name, same as this, it's a geo, see, this is one that's been sliced. If you slice that up, this is a little prettier color than that one, but,
That's a dinosaur?
no, I just made that up about dinosaur egg, sorry. Not really, but sort of.
The rock? What kind of rock is it?
It's probably a composite of several things. These are called, oh goodness, what can I not think of the name of that? Geo, I think of his name. What else was thinking about it? Now it's blue too. Geode, just a geode, that's what it's called. It's the old gray cells and what we used to do. They never were very good.
Who gave it that blue color?
The type of mineral that's in it, what was this? I'm trying to remember which is the blue one. rinse my hands off and come back to clean the table off.
Okay.
Something that's got a bunch of colors says, the first thing that says is colorless.
Okay. Either get in with a group that's there or find out from them how to do it.
Oh, yeah. Why was that? You want to do it?
It's so easy. Oh, you're so nice.
Get on my nerves.
You finished? Huh?
Yeah.
Oh, good deal.
Oh, this is.
I was going to give you a show on this. Are you still working on it? This, I think, is mostly quartz. I think they call it quartz. Notice the large crystal size. It's slow cooling. Cooled slowly. Somebody, let me, before I forget. That's, I think, is quartz, pretty much quartz.
It's like it, looks like it, right?
Yeah, it probably got shattered there, you know, broken apart somehow. These are breaking along the cleavage planes. See, the cleavage planes are smooth planes like that. This, I think, also is quartz. It's a little easier to see the hexagonal.
Yeah, it looks like it broke here and here.
Right. And these are just hexagonal crystals. So you can see that six-shaped thing at the top. And so all these are those prismatic crystals.
This one's lighter than the other.
Yeah, well, it's smaller, is part of the reason. It would be interesting to measure the densities. I bet you the densities will come out pretty close to the same. This is lighter because it's smaller. Okay. Now these three, and we'll talk about this later today, are three samples of what we call sandstone. I think you can sort of get a guess of what we call a sandstone. Made up of sand particles pressed together. And you can feel it, it has a rough texture to it. Now, I'm not certain this is sandstone, but I'm guessing it is. So it can be different sizes. This one I'm sure is sandstone. Something different about it. We'll be talking about it today.
Looks like that one rumbles.
Yes, it really does. You hit it right on the nose. And we'll talk about why that's the case today in class. Okay? I'll come back to it. If we go over here and look at
Okay, what's the thing?
yeah.
Oh, essence. Okay, go back. Okay.
Okay. These are examples of what we call geodes. And they broke. They're pretty fragile. But you can see the crystals in them. Like I said, I was careless with actually what I was using it for is something that's to keep from putting stuff down on the counter, you know, sort of as a coaster. Yeah. And I picked up my bowl or my cup or something like that, it stuck to the bottom and fell and broke. So, but this is called a geode. That's one type of mineral inside, and others on the outside. Now, they polished this one. Yeah, it really does. That's a, and here's another one that this is even more fractured, but you see. Yeah, I think that's great. I know. I can't remember. What's that?
Almost on a steamboat.
Almost.
Almost on a steamboat.
Yeah. Well, you can have it if you want it. I don't care.
Really?
Yeah, sure. Yeah. Now, this is just an old rock, and of course, yes, exactly. Brittany thought it was a dinosaur, but let me show you what it really is. It actually broke. And what is it inside? A geode. If you were to yeah, it really does. If you slice this evenly, it would be like that. Not as pretty a color, but gray on the outside, and sort of a taupe there, and then a sort of clearish, and then different things. So you see, that is what a geode. That's what that looked like at one time. It was a much bigger one of these, and someone just happened to slice it and find out, wow, look at those colors.
So they don't always. How does it get to look like this glassy?
Yeah.
I started.
The what?
Why does it look like glass like this?
Okay, well, one thing, they did polish it. They did. This one definitely wasn't polished, but you see, if you polish that up, you can almost feel how smooth it is naturally.
If you rub it a little bit, you can see the glass.
Yes, the glassy nature of it. And so yeah, that's what we call a geode. And you can see the crystals near the center. I mean, those are definite crystal things. It's largely come about by a chemical thing. The something in the middle draws different chemicals to it, and they separate according to the chemical reactions going on. Yeah, it's just a rock, but it's a rock made up of, and we'll talk about this today if we haven't already. Well, we already did, made up of different kinds of minerals. These, the minerals have actually separated chemically, you know, so you can tell that's one mineral, that's a mineral, that's a mineral. and then this is some other mineral on the side, or else that's just another rock inside. But the formation process gave it those rings. Now, these here, I'm not even sure what they are. It may be a piece of something like marble. It has those characteristics to it, but it's definitely not sandstone feel. It may be it's a mudstone or a siltstone.
I'm going to share
Oh, absolutely. It was part of the bigger rock. Now this, you can tell, has a lot of quartz in it. That may be a piece of granite, would be my guess on that. It just hasn't been polished or anything else. Yeah. Remember when we were talking about the fact that color is not a good
You can look
indicator.
on where the minerals are. They
If
have.
you're looking at this, you call it dark brown, right?
You can look like, if the mineral is, you can say quartz.
And you see inside, it's not a dark brown. So that may be just a inclusion of organic matter or something else. Color is a terrible thing to try to classify minerals. I think maybe so.
It's probably like in a river or something.
Right, it could have been. I just don't know where they came up with this. I had figured out the puzzle of it, but now I can't. Huh? Okay, but I was, oh, this should be over on the other table. Oh, I got something, I brought this up. It's all right, it's not working. This is, I'm pretty certain, it's just a piece of coal.
Really?
Now, how do you classify coal? Is that a mineral or not a mineral?
Really? Don't you think coal counts?
It's what?
Don't you think it's a mineral?
Okay, it may not be because it was made from organic thing, non-organic. Minerals are supposed to be non-organic. But it was so long ago, it does seem to have sort of
Yeah, but I mean.
crystal structure that you would think might be a mineral.
Pencil weapon.
Yeah, but it could be very soft. Remember, talcum powder is a mineral.
Oh, yeah.
Yeah, and it's really, really soft. Your fingernails, Jim's in your fingernails. So yeah, you can't tell by how soft or light or low density, anything else. This is,
It's like that's the plain chunk of marble.
yeah, you're close. It's granite, okay? But, we're gonna get some marble over there. Want to take this out. This is a granite. Now remember what we said about granite? One thing is light color. Certainly fits the deal there.
Looks like this might have been tiled.
It actually was part of a slab they were using for a countertop, but they broke it. Yeah, and they polished that one. The rest of it is not polished. And that's why I think that looks sort of like this. Yeah.
Yeah, actually, it might, looks like it might have cracked off.
It did. They broke it and they gave me this. It's where we got our countertops at our house. We got a type of marble. I don't have a sample of that. So I said, I teach a physical science class and I like to show you. Oh yeah, come get these are just scrap pieces. And he just gave me a bunch of these. Now you see granite does have some dark areas in it because it's a mixture. That's probably some biotite in there. Lots of quartz in there. And, the sort of the tannish color, some of your other minerals. Now they call this also a granite. I'll do this one next. And that probably is a granite, but it's a lot more of the iron stuff in it. A whole lot more. What's that? Yeah, it could be. And that has more of your feldspars and those kind of things in it because you have the granite color. So that can still be a granite even though it's not all that light color. Now, this one, I have real problems with calling that granite, because this is really dark for a granite. It doesn't look dark, huh?
That looks more like the song.
Yeah. And that looks like could be granite. But man, when they polish it, that's awfully dark for a granite. But it still could be. It could be one with high type concentration in it. Yes. How are y'all doing on the lab? About halfway through. Technically, they have until 3, but I think they'll be finished before 3. Estimate on yeah. Okay, ETC, estimated time of completion. Okay, most people are finishing now. If you need to go take a quick break, we'll be. Okay, all right. Okay, so that is, they call it a granite, whether it really is or not, I don't know. But what I do know, it does have large crystal sizes. Look at those. You can see big old crystals in there.
Yeah, right here to the right here.
Yeah, exactly. So that does lend to that could be a granite. I'm not
I
convinced.
think granite's probably just turned in like agile.
I know, yeah, it's sort of like Kleenex, you know, they call everything.
Yeah.
All right, so that I'm pretty sure is legitimately a granite. That is legitimately a granite. That one I'm not sure about. What's that? Hopefully we'll finish on the video. This is the stone we use in our bathroom. This is the one I was talking about. This is a type of,
That's the one that's
yeah.
they call black granite.
Yeah, black granite, and it's definitely not a granite. No granite is that dark. And notice it's real small crystal sizes. That's a basalt.
Yeah, this is definitely.
Yeah. Okay. And we'll be talking about, in fact, using this in a later lab too. We use this in one of the granite pieces, probably that one. Okay. This one, that over here.
Let me tell you.
No, I was just going to say, because you can turn on and see it too. These could all be 3 pieces of coal. This is probably not as high a quality coal, but it's so light. It's not dark because of iron. I think it's dark because of carbon. That's got to be coal. Okay. And I'm not sure what these 3 are. Someone brought them in, and I'm not sure. They are very porous. I would almost think that these are a type of lava rock that cooled at the surface and got air in the middle of them. Okay? Because that's really yes, it really does. So I'm thinking it could be dark color from iron, and it's just got a lot of, like you said, air pockets in it. This must have surrounded some other rock when it was cooling, and it picked up something else in it too. But I don't know for sure.
This one looks like it's got still shine.
Yeah, but that could be coal too, because that's definitely not iron. Feel how light that is. That can't be iron. So this one, I think is too light too. I think this must be coal or carbonaceous type material.
I'm gonna hold it when it's on this.
I don't know. Sometimes it's just that's the way it is. I don't know why it is, but it's
It's like it's rough right here and here, on the bottom, top right there.
Yeah.
Almost glass-like.
it is, and I can't imagine mining and having to walk on something like that. I would think that's really dumb. Now here are the marbles. These are 2 types of marble. One of them is from Italy. They're both from Italy. These are pretty heavy. Okay. Yeah.
This is probably what they use to kind of model they use to film, right?
Yeah, definitely. This was again, I think it was a countertop that it broke. So, or maybe they're cutting off it in and it broke something. So. Okay. Now they actually call this Chap18, and I think what Chap18 is marble before it became marble. Okay. It has a, yeah, second. Proto marble, that would be, I was going to say, the earlier stage of marble. I think that's how I would classify it. I don't know if they classify it that way. Now, what was marble before it was marble? It was limestone.
Yeah.
Yeah. And this is a piece of
Yeah,
limestone.
if you line those way up, they
Yeah.
form a perfect before and after.
Yes, that's before this middle and these two after. Yeah, you're absolutely right. Because and we'll talk about that in today's lecture.
It almost looks like it's only 20.
Yes, it is. I don't know. I got it from the same place that someone must have had some limestone they were doing something with. It was a piece they cut off or something. So anyway, how are we doing? Is pretty much everybody through? Still got a little bit to go? Let me bring the other one. These I don't know how to classify them. That is awfully slick, so I'm guessing that's a mudstone or a siltstone, but I'm just guessing on that.
This looks like, parked by my house, it's a little river, and this is
Yeah.
like the kind of rocks you park down.
I wouldn't be surprised. And this one is very lightweight, and it almost looks like that could be a geode.
Yeah,
But when you
it
break-
looks like another one.
Yeah, but when you break it open, you'll see there's no geode characteristic in it. Just more
Maybe
the
there
same.
was one before it finished.
Yeah, it could be. But it doesn't have the grittiness like these sandstones, so that's why I'm guessing it's probably mudstone or siltstone.
Yeah, it looks like it probably been rock smooth on this side.
A lot of time when you see that smoothness like that, that means it's been interacting with water. So water will sand things off pretty smoothly. And that, I think they just call this chert. It's mostly quartzy type material, but
Yeah, it doesn't have torque.
yeah, you're absolutely right. You nailed it. Good deal. Okay. We'll be saying a lot of this again in class, but
When you deal with history, you deal with rock.
I guess you do, design. Is that your major history?
Yeah, so I can see, I can tell, I've seen it in buildings.
Right, exactly. Yeah.
Like Egypt use a lot of basalt stuff when they
Oh.
call it statues.
Right, okay, I didn't know that. Yeah, fine grain that would enable them to
Yeah, I mean, they also use quartz a lot.
Yeah.
And limestone.
limestone for sure, yeah. And those are different types. We mentioned basalt, that's an igneous rock. Quartz is an igneous rock, but it's a non-ferromagnesium igneous rock. Limestone is a sedimentary rock, so
I would probably get all those in the
Yeah.
desert, though.
probably, yeah, you could probably find those. I'm gonna go wash my hands again.
I should probably wash mine.
Okay, if you'd like to, I'll hold the doors if you need me.
Yeah, I could.
Okay. I know that some of you told me you were through already. You're welcome to go around and look at some of the rock and mineral samples that we have here. They're mostly rock. There's a couple of them are pretty purely minerals. Yeah, we think this is sandstone. We'll be talking about that today. Yes, it is.
I didn't see
We'll be talking about the differences. These are also sandstone. This hangs together a lot better than that. Yeah, and that I think is sandstone too.
that one might have a fresh one.
You're absolutely right. You're already given today's lecture. You're cheating, okay? All right. And these,
Yeah, just like the History Channel.
Yeah.
Tell me about this stuff stinks.
I think these are both pretty good samples of quartz material. For sure, this, you can see those hexagonal crystals. Now the base down here may be something like limestone, but that looks like quartz there too. But this just looks like a different material that fits to it. But remember, rocks are combinations of different kinds of minerals, okay? And then we got others. How are we doing? Most people finished? Okay. Okay, limonite, those are the two I mentioned. You need to look it up and see if you can find, did you do a search for limonite? Oh, okay. Okay, try this one up here. I don't know if that's any better or not. Looks like all these are different kinds of limonite, okay? So you can pick one, and then write that as that's the one you're going to do. You might want to do rancite if you wanted to. And if you find what you're looking for there, yeah, it looks like it's got it. So write rancite above it there. R-A-N-C-I. I-E-I-T-E. That's the form of limonite. See, that's a big class of minerals. And see the same thing, what was that other one, hornblende? No, feldspar, yeah, hornblende specific feldspar. Okay. Oh, and the other thing, folks, I'll apologize ahead of time. Sorry I left the projector on while people were working on their lab. They, there was a lot of dead time there, but maybe you overheard some of what was being discussed or said or whatever. One question I think that came up after I turned it off, so I did want everybody at home to hear this too. Don't forget on page 331, the page before your tables that you fill out, there is a question. It says, what's the purpose of this lab accomplished? Why or why not? And again, you don't have to write much about it. Maybe an answer, maybe a sentence or two. That would do fine, okay? But anyway, don't forget to answer that question as well. Okay. So, all right, let's be sure you return the computers to whatever state you found them, but you can leave them on during the lecture if you find it helpful. So, I think we left off here last time. We were talking about sedimentary rocks. Can someone remind me what the two big classifications of sedimentary rocks are? Sedimentary rock. Two classifications.
Shell.
Say again?
I don't think I'm right. Shell.
Shale is a type, but that we haven't even gotten to that yet, okay? It's the type of things being sedimented. Say again? Clastic and chemical. Clastic would be like sandstone, mudstone, siltstone, actual materials, conglomerate, breccia, we named several. In fact, these pictures here, this is a piece of sandstone. Those who came around and checked, I have 3 pieces of sandstone here. You can feel the roughness of the texture. Sand. Sand is the stuff that feels gritty when you rub it between your fingers. Okay? This is a piece of breccia. Remember, breccia is made from the large particles. It's a clastic sediment, and this is actually gravel pieces in there, bigger than sand grains, gravel pieces. What's the difference in breccia and conglomerate? You're looking at breccia. Hint, hint. Breccia has the sharp angles to the pieces. Conglomerate would be rounded pieces. Otherwise the same. Gravel in some type of a structure that makes a rock, that would be, I don't have an example of breccia, this is the closest you're going to get. Now, this one right here is limestone. We do have a sample of limestone, sort of it looks like a doorstop, okay? Back there it's a sort of a angular piece, and that looks just like this. But that's not a clastic sediment, that is a chemical sediment. The materials came out of solution, okay? Now, but remember, rocks are made up of mixtures of other things. This piece of rock, for instance, this right here looks like it's a fossilized seashell. So that wouldn't be a mineral because it's organic, or it was organic, but it's is part of the limestone. The other stuff came out of solution around that and surrounded it. And probably this could easily be a little chunk of seashell or something else like that. Okay? So those are pictures, pretty nice pictures of sedimentary rocks. 1 chemical, 2 clastic. Clastic meaning actually particles. Okay. Any questions on that? Now, before we move on, I did want to remind you of a couple of things. We mentioned asbestos. There is a blurb, a closer look on the top of page 447, talking about asbestos. Asbestos is sort of like what y'all ran into with limonite and feldspar. It's a class of things. There's a whole bunch of things that are called limonite, even more things that are called feldspar. And what you were to do on your lab was find one of the classifications of that and then write up your physical properties of that one. And, write which one you're writing on. Like feldspar, you could have plagioclase, you could have orthoclase, you could have lots of different ones there. So that was what you're supposed to do. Now, danger asbestos, we usually think that, but if you read through here, you'll find out that some asbestos is perfectly safe, okay? But it's just really hard to tell them apart. I think that's in this one, okay? All right. I think we're ready for the next slide. Oh, let me get... Say it again? It can. The bad kind, that's exactly the problem with it. Okay, let me... I'm pretty sure that's the disease that comes from that. Okay, goodness gracious. Whew. Shock, shock. I think I recognize this guy from somewhere. Okay. Right here. Here's today's lab. You need the last lab too?
Yes, sir.
Does anyone else need the previous lab? The one on the moon that no one's turned in yet because you... Oh, I didn't want to say that about... Oh, here it is. Okay. Wrong stack. Okay. Okay. Here's the moon lab. you'll need to listen to the YouTube video, and it'll describe everything you need to do on both of those. The one for today's lab, you won't be able to hear it until I get it uploaded, which will probably be tomorrow afternoon sometime.
Have I missed a test?
Yeah, probably. Well, let me see. I don't remember. Did you do test 3?
I've only done 2.
Huh?
I think I've only done 2.
Okay, yeah. The third test is the only one you missed in. So you'll need to make that up. Okay. Now, I think I mentioned to you before, this slide you're going to see several times. Okay, but this is just reminding. Clastic sediments, that means what? Made from particles. They could be big particles, medium-sized particles, little particles. Conglomerate or breccia, larger than sand size. There it is, right there, breccia. Conglomerate would be rounded. Okay. Oh, I did all that and I forgot to mark you present. So you used to not. No, I didn't say that. All right, Carl is here. Yeah, I don't have your test 3. Still missing Josh. And still missing Darius. Okay, the rest are here. Okay, now we did lab first today, Carl, rather than wait till the end, because we needed the computers. So you'll need a computer at home or here or somewhere to do the lab. Okay, and you'll hear it all if you go out there. Okay, so clastic made out of particles. Large particle size, medium particle size. Gravel particles, sand particles. Okay? Now we'll talk about the stuff that goes into that later. The cementing agents, we'll talk about that later. Chemical sediments, though, would be things like limestone, calcite, which comes out of solution and forms the thing. These are actually particles, these are out of chemicals. Calcite, dolomite, gypsum, which would be calcium sulfate, halite, sodium chloride. Those are the types of salt, of chemical. Here's Darius. Goodness, you just keep me guessing, huh? Here is today's lab. Did you get the moon lab? You were here that day, weren't you, or were you? Okay, yeah. Okay. Oh, I was going to say this about the moon lab. Before I forget it. I saw a little sliver of a crescent moon night before last. And I said, it's getting close to time. If you're an evening person, you're soon going to be able to see the moon. Remember, you pick the time, and you pick your place, and then start making your observation. Now, if you're a morning person, you're probably near the end of the time that you'll be able to see the moon. But if you're going to be an evening person, if it's early evening, I think I was seeing it as maybe as early as 7 or 8 the last 2 nights. If you're shooting for 10, you might not see it at 10 because it may have already set by then. But watch for it. Okay, this is the time. Yeah.
Did you see it was like a star? I don't know if it was a star or a planet. It was like directly above the moon. Did you see it?
No, I didn't know. Last night when I did see it, I was in the car, so I just saw it when I was doing it. I didn't have a chance to get out and really look at it carefully.
It was really nice.
Yeah, but you can probably start your moon lab, the observation. You can do that other part that we did in class anytime, but you can start those observations, if not now, very soon. Watch for it each night. Don't let a clear night go by without trying to detect it, okay? So, I think we beat this one to death, haven't we? Okay, those are the types and classifications of sedimentary rock. How do sedimentary rocks, and basically lots of rocks, come about? Well, if you haven't picked up on it yet, litho basically means rock, okay? That's a prefix. I don't know if it's Greek or Latin or where it comes from, but that usually means rock. So this is sort of the rock forming process. Lithification, the rock forming process. Now, we're talking about sedimentary rocks now. Here are the 2 main parts, especially of your clastic sediments. The clastic sediments are made out of particles. Okay? The first of these is compaction. Okay? The sediments happen let's say it's in a stream, wherever it is, the sediments falls out of the water or out of the wherever it is and starts settling down. Okay? So you have the settling. More stuff settles on top of the previous stuff. And it keeps settling, and as it settles, it compacts the layers beneath it. Okay? The extra weight above compacts the others. Reduces the thickness of the deposit. It may have been like this to begin with, may get it down to like that, or bigger, whatever. In reducing the thickness, it's reducing, and this is a soils term that we'll use in a later chapter, reducing the porosity or the pore space. Well, the pore space is generally filled with air or water. And if this is deposits made in water, most of those pores are filled with water. So when you compact it, you're making the particles get closer together, making less pore space, squeezing out the water. Now, what was that water doing in there? Well, it was just hanging around mostly, except some of that water may have had other stuff dissolved in it. Most water does have stuff dissolved in it. And some of that stuff dissolved in it may have been cementing agents. So the second part, after compaction, you get cementation. The spaces between those sediments, okay, particles, are filled with a chemical. Let's say maybe that chemical was calcium sulfate, calcium carbonate, something that's easily dissolved in water. The water gets squeezed out. Some of it evaporates, leaving that cementing agent. Where do we use calcium carbonate and calcium sulfate?
Brick wall.
Brick. It's the mortar that goes in between the blocks. It is a cementing agent. It cements. In fact, it makes cement. That's what it's made of, okay? So it's a cementing agent, but nature does it, and the chemical deposit binds the particles together. So let's first go back and look at the previous slide. That's what this stuff is. That's the cementing agent in between these. That's one rock. That's not a group of little rocks. That's one rock made up of these fragments, gravel fragments, plus the cementing agent that's holding it all together. That's what we're talking about. Okay? Now, here's the picture. Your sediments, they pile on. Now, they did these colors in particular, okay? These, I don't agree with this. I would say the whitish ones are quartzy, the pinkish ones are feldspar, the grayish ones are something else, okay? But I think quartz is being white, okay? But you see, a rock is made up of several different kinds of minerals and other stuff. Remember, that's how we defined a rock. The other stuff may be the cementing agents. Different types of minerals, okay? And when it's first labeled there, you see how big the pores are? You get more and more pressure on top. They get squeezed down, so you have less and less pore space. Most of what was in the pore was water. Now the water is squeezed out, but hopefully it's left some coatings behind, and those coatings are your cementing agents. Now, for those who did come by and pay attention to our sandstones, these two pieces of sandstone, and I think Brendan pointed this right in front. They probably got pressed together more tightly. Yes, the compaction was better. This one is leaving grit all over on your table, right? Because this one either didn't have as much compaction or the cementing agents weren't as strong. Or it didn't have as much cementing agent. I don't know which is which. If you probably did a density of those, and if the density came out the same, you would have to conclude probably the compaction, the cementing agents were not as strong. If the density in the powdery one was less, then it didn't get compacted as much. Okay? That's the two processes. Compaction, cementation, and they sort of go together to a certain extent. Any questions? The lithification process, the making of the rock forming process for your sedimentary rocks, especially your clastic sediments. Clastic meaning Oh boy, forgot it already, huh? Clastic meaning particles, particles. They could be small or big or in between or tiny. Okay. Now, a couple of pictures in the book that were not in the slide set. On page 448 or somewhere thereabouts, limestone. Okay? And frankly, if you look at most of the road cuts, say on I-65, I-20 and 59, most of those road cuts, what you're going to see, the rock that are on the edges there when they cut through the side of a hill or mountain or whatever, most of that's going to be limestone. Okay? Don't think of limestone as all light colored. It can have, just like Brendan and I were talking about while y'all were finishing up, on one eye here. It can have coatings on it that make it look dark. All the king's horses and all the king's men. Okay. Oh, that may be it right there. On the surface, those of you can see, this looks like a pretty dark rock. But remember, we don't count color as really good classifier. Okay? Because when this broke off, look at that, much lighter inside. So you can have coatings. And a lot of that limestone that you see along the side of the road is dark looking. And you're like, is that coal? Probably not. More than likely limestone. It's just that it's had algae growth, molds, all sorts of things. So limestone's pretty rich in nutrient, and that's why we have pretty good soils here. Our underlying parent material is limestone. That's what makes the soils that we have to farm with. Poor Georgia, next door, underlain mostly by granite, acidic igneous rock, not a lot of mineral nutrient there. So they don't have naturally as rich a soils as we do. So we're ready now, I guess, to move to metamorphic rocks. Okay? What do we mean by metamorphic?
It's changing.
Changing, excellent, okay? Morph is to make, okay? Morph into something, you know, and meta is major change, okay? That's a rough definition. If I can remember the first place I heard the term metamorphosis. Do you remember the first place you heard it?
Biology?
Say again?
Is it biology?
In biology, probably. What was a little fuzzy caterpillar changed into a butterfly, big, beautiful butterfly. That's metamorphosis, a major change, okay? Same animal, but just changed big time. For those of you who are interested in the Bible, when you talk about a major change, goodness, I can't think of the verse right now. Be ye transformed. Romans 1:12, 1 and 2. Don't be conformed, but be transformed. The word there is metamorphosized, okay? Major change, okay? For any of you who are classic, goodness, I can't think of the author. German author, weird. I don't really like reading them at all. Very famous, but I can't think. One of his most famous stories, the title of it was Metamorphosis. Do you know who that was? Okay, I thought someone called it out, okay? I can't, say again?
Wagner?
Not Wagner, he was a composer. Yeah, he may have done a symphony after that, I don't know. But the story was this creepy guy turned into a cockroach. That was the metamorphosis. You know, weird, you know. I'll think of the guy's name right as soon as class is over. So when we're talking about metamorphic rock, yes?
H.G.
No, not that weird. No, I mean, yeah, probably weirder than him. Okay. This was a German, I'm pretty sure. He wrote about the same time as Kafka, you got it. Yeah, Franz Kafka, I believe it was, who wrote Metamorphosis. Was he German or was he, I think he was German, yeah. Okay, so metamorphic rocks are rocks that have changed big time, okay? Previously existing rocks, now what changes a rock? Say again? Heat, pressure, hot solutions, something like this. Heat, hot solutions, that's involved in there too. It's changed the structure of the rock. Okay, we'll get to one. I just can't wait. Okay, the causes are associated with geological events. Now remember the sedimentary rocks, let's start with that one. Anyway, they were more pressure, pushed them together, compacted, cementation, that changed. But it wasn't a rock before, it was sand, it was silt, it was clay, it was gravel, it was something else before. That was a major change, but it just changed into a rock. But if you take that same sedimentary rock and add more pressure and more heat, say it gets pressed way down into the earth structure and starts getting some of that heat from the inner part of the earth, we'll talk about that in a later chapter, then you're changing. What you're changing is the chemical makeup of that rock. These geodes we have here, they, pieces of geodes I have left here, okay, they were some sort of chemical reaction going on. It started at the center and worked its way out. Basically, oxidation reduction reactions, other types of reactions, they form this, and you get the beautiful colors because you have different concentrations of minerals left when some come out of solution. It changes chemically. Well, that's what's happening in metamorphic rock. The heat, the pressure, those hot solutions are changing chemically the rock that was there into something else. Okay? Now, what are causes of those? Usually geologic events, such as movement of the crust. What do we call that? Earthquakes, exactly. Anything that can move the crust of the earth, the plates of the earth, there's a lot of heat, there's a lot of pressure that are going on there. Heating and hot solutions from magma intrusions, that would be volcanic activity. Yeah, y'all got it, okay? And temperatures must be high enough to cause recrystallation, but not melting. You can heat a rock and get it so hot under so much pressure, the crystal structure actually changes, but it remains a crystal. You add too much heat, you melt it. If it comes back out of solution, then what kind of rock is it? From molten materials. Igneous, okay? So that wouldn't be metamorphic. Metamorphic, you heat it a lot, but not enough to melt it. And that heating changes the chemical structure. Recrystallization. Here is the sort of a classic table of this. And you'll run into this. I think you see this table more than once. Okay. We're going to start with a sedimentary rock, shale. I think someone mentioned that earlier. Shale. Shale is basically mud, so it's largely either silt or clays that have sedimented out, usually in sheets. That's what makes shale, the sheets. Well, you add enough heat and pressure to that, you compress that shale, heat it up, it changes its chemical structure somewhat, and now you have slate. What do you think of when you hear slate? Our church has some slate roofs, tiles on the roof. They're actually made out of rock that cut into plates almost, you know. And around New Orleans, a lot of the buildings there have slate roofs. They started doing that because they had major fire down there quite a long time ago, and all the houses burned, and it started on the roofs, okay? They have lightning down there and stuff, so they started making a lot of their older houses then had slate roofs. Yeah.
It's just rock, they don't do anything to it, or
The what?
they don't do anything to it, it's just
Okay. Remember when you're cutting crystals, you try to find those crystal planes, so they cut them into sheets, and then they shape the sheets how they want them, cut them into rectangular things, and then they put them in just like they do asphalt tiles, except asphalt tiles are flexible. These are sheets. It's like a tiled roof. It's only a tile is made out of, you make the tile. This is made out of shale, a slate, which actually nature made for you. You just cut it into the shape you want. Okay. So that sedimentary rock became metamorphic rock. The heat and the pressure changed the crystallization. Now, after that, it becomes schist. Add more heat, more pressure, and now you start getting a little bit of warping. The shale was flat, and the slate was flat, but when you add more heat and pressure, you actually sort of warp, so your schist is not always these nice clean sheets like you had before. When your mom changes the bed. No, that's not what we're talking about. Okay. It doesn't have even sheets necessarily. But you add more heat and more pressure, deeper and deeper, and suddenly you get another change of crystallization, and that forms gneiss. Gneiss rock. No, I'm just kidding. The G is silent, okay? And remember that picture we saw early in the chapter of the rock that had all that curved and stuff, big old chunk of rock? That was gneiss. That had been shale, became slate, metamorphosized to slate, metamorphosized again to schist, and then metamorphosized again to gneiss. You could tell there had been layers there, but now they were all warped and interwoven. Really a pretty rock. Now, you add more heat, more pressure. More heat, unfortunately, is going to do what? Melt it. And then it becomes granite. What kind of rock is granite? Igneous rock, okay? So you can get granite that way. You had a shale that's made up mostly of mud, silt, clays, compaction, compression, made it into sedimentary rock, shale, pressure and temperature, made it into metamorphic rock slate, more pressure, more temperature, sort of started distorting it some, made it into schist, and then the schist got more heat, more pressure, and made it into gneiss, and then the gneiss got more heat and started melting, went back to being granite. And some of those things that were the particles in the shale may have come from granite rock before that. So it's all a big cycle. Everything's a big cycle. Okay. Another one that we have samples of here. What kind of rock is limestone? Oh my goodness, it was so long ago. What kind of rock is limestone? Sedimentary rock. What kind of sedimentary rock? No, that was the shale. This is chemical. The limestone was chemical. We have a piece of limestone right here. This is Indiana limestone. Okay? You have to look at it, pass it around, whatever. Indiana limestone. Okay? It was sedimentary rock, chemical sediments, but it got buried and buried and buried. Lots of pressure, lots of heat. What happened to that chemical sedimentary rock? It became marble. And field marble. Any differences here? Yes, big differences. Where did it come from? That you changed the recrystallization of the limestone, and now you're marble. Notice a lot of pore space got pressed out. That's from the pressure, and the recrystallization happened much harder. Limestone is much harder than, marble is much harder than limestone. However, what's a problem with limestone? Anyone know? Some buildings downtown, I think the courthouse is made out of limestone. Say again? I'm sorry.
So, what you want to know about it?
Yeah, what do you know about limestone? Any problems with using it as a building material?
It deteriorates.
It deteriorates. Why?
It's made out of chemicals.
Okay, everything's made out of chemicals, but specifically, what happens is it's calcium carbonate. Remember? Calcium carbonate, you put an acid on it, and it bubbles, it fizzes. And that then you change the calcium and carbon dioxide. Air bubbles away. Well, acid rain that has nitric acid in it, sulfuric acid in it, it's going to deteriorate the limestone. Unfortunately, marble will too. Marble is harder, it takes a little longer, but it will etch. And we have marble countertops at home. In fact, the marble in our countertops came from Sylacauga, Alabama. It's called Alabama White. A really, really pretty limestone. Okay? Problem with it, it's made out of, it's a really pretty marble. Made out of limestone. If we get acid on it, and a couple times my wife has had coffee drops on it, coffee's a little acidic, it etches it just a little bit. We try to get it up soon. I probably spill a little vinegar, getting a pickle out of a jar or something like that. If you don't get that up soon, it will etch it slightly. In time, it's not that nice polished surface anymore. It's got little etching. It's going to last a long time, but it will discolor because the chemical gets down into it. So marble is metamorphosized limestone. Okay. You add more heat and more pressure to marble, what is it going to do? Melt, and when it melts and then recrystallizes, you get calcite. This is calcium carbonate, which is calcite. This is calcite. Remember the calcite you saw, very first one on your lab today? The little crystals we had? What happened to those little crystals? They're over here. No? Are they there? No, that's not them. Those nice, pretty chunks of them. So not everybody was here. Where did they go? What did I do with it? I just lose my head. Huh? No, those are the geodes that may have some calcite in them. The white rings probably are calcite. Those chunks. Are they in here? Oh, did I put them back in here? Oh, yeah, I'm sorry. I didn't mean to do that. This was the calcite. Okay? Those crystals. Remember those pretty crystals? That's calcite. Okay? Came back out of solution. So that may be a chemical sediment again. It may be. That calcite might be chemical sediment again. Okay. Sandstone. What you reckon it is? What kind of rock? Three type, igneous, sedimentary, metamorphic. What is sandstone?
Metamorphic.
Not yet. Say again? Sedimentary. Sand settled out, got compacted together, got chemically cemented together, and made sandstone. That's that rough stone that we have right next to a Carl there. Okay? That one, that one takes the sand off easily. The other two are both sandstone. Okay? So it's a sedimentary. What kind of sedimentary rock? The particles, what do we call that? Clastic, exactly. Okay? Clastic sedimentary rock, but it gets more pressure, more heat, more temperature, and it becomes quartzite, which is a form. It looks sort of like, well, not a lot like, but it's made out of the same material as a quartz, but it's now a metamorphic rock. The chemical structure of sandstone has changed, it recrystallized into quartzite. You add more heat, more temperature, more pressure. What happens to it? It melts. And then when it recrystallizes from melting, it becomes quartz, which is igneous rock. So quartzite is metamorphic rock, sandstone that was recrystallized with heat and pressure without melting, but once you added enough to melt it, then it comes back out of solution as quartz, which is an igneous rock. So, let's go to another, they don't name it, of igneous, fine-grained igneous rock. Name me a fine-grained igneous rock. We talked about them several times. We have a sample of them here. Fine-grained igneous rock. My bathroom rock. Basalt. The basalt is a fine-grained igneous rock. So let's just assume it's a basalt. You add a lot of pressure and a lot of heat to a basalt, and you could change the recrystallization, the chemical structure of it, and make it into a schist. This schist came from sedimentary rock. This one came from igneous rock. Okay? Add more heat, more pressure, it becomes nice as well. This gneiss probably won't have the layering that you saw in this one because that was from sedimentary. This is from igneous. You don't have layering in igneous rock. Okay? So you get gneiss and you heat it some more, and what happens to it? It melts. And if it recrystallizes, it becomes granite. But granite is a coarse crystal. You started with basalt, wound up with granite. Now, it would be basalt and granite. That's wrong. Because basalt's high iron content, granite's low iron content. It could start as basalt and wind up as gabbro, okay? Or it could start as, I can't remember, the fine-grained, light-colored rock that would then later become, granite, okay? But anyway, that's the process. It's all a cycle. We're going to talk about that in just a couple slides. Any question on that before I move on? Okay, before we turn the page, there's a Science and Society blurb here called Using Mineral Resources. And this is the one talking about phosphate resources. Phosphate, which is one of the 3 major minerals needed for plant growth, agricultural production. And it's the one that we mine. It's the one that comes out of the ground. Now, potassium, potash they call it, comes from the ground too, but there's plenty of that, generally. Getting harder to get, but it's plenty of it. Phosphate, not plenty of it. And it's getting harder and harder to get to. How are we going to feed the billions of people that live on the earth if we can't get the phosphate? We could have a disaster happen. Now, I talked last time about the guy who was able to figure out a way to get nitrogen fertilizer, and that was a big, big deal because you mine the Chilean nitrate, the sodium nitrate, and that's what we use for nitrogen fertilizers for probably decades, okay? But we're running out of it. Hans, goodness, I'm going to blank on his name now. We talked about him last time. Goodness gracious. Haber, Franz Haber, the Haber process. He was able to take methane and I guess it was just nitrogen gas, methane and nitrogen gas, or one of the nitrogen oxides. There's plenty of nitrogen around. The air in this room is what? Almost 80% nitrogen. There's lots of nitrogen all over the place, okay? So he was able to combine with methane, a lot of pressure, a lot of temperature, with nitrogen, or some oxide of nitrogen, and form ammonia. And with that ammonia, you have a fertilizer. Ammonium hydroxide, ammonium chloride, ammonium nitrate. There's just lots of ammonium fertilizers, pure ammonia. Have a question?
Actually, yeah, I was going to tell you.
What's that?
It's 3 o'clock.
Oh, it's 3 o'clock. Oh, goodness. The timekeeper has caught me. Okay. Okay. We'll, let's finish this and we'll move on to the other classroom. And so Haber discovered a way to manufacture nitrogen fertilizer out of air and methane in a pretty expensive process. So it's not cheap, but it sure is a lot more plentiful than what just using sodium nitrate you mine out of the ground. And where did that sodium nitrate come from? Bat poop, okay, guano, okay? That's where they mined it from. Caves that used to have lots and lots of bats for years and years and years. We were using it up like crazy, so we were running out of it. He found that. Potassium chloride, there's lots of sources for that. That's potash, that's the other one. But phosphates, no, they're hard to get, hard to manage. Even once you get the apatite rock that contains the phosphate, you have to treat it with concentrated sulfuric acid, get it so it's somewhat soluble, and then you move on from there. And it's an expensive, difficult process, and we're using it up faster than we can know what to do with it. We aren't going to be able to feed the world if we can't get the phosphate. So that's what this blurb is talking about. Now, I happen to have a friend of mine. He's a missionary to Cameroon, which is north of the Congo in Central Africa. And he said that the folks there have found this plant. It's not a very pretty plant. It's not a certainly not an attractive plant. There's no food you can eat from it or anything else. But you know what that plant does? It mines the phosphate out of the soil that most plants can't get to, and then stores it in its material. The bark, the wood, the leaves, and stuff like that. You can take that plant, grind it up, use it as a fertilizer. There's your available phosphate. Now, can we do that on a large scale? I don't know. That plant may be only specific to that area. But man, we got to do something, or else we're going to have a bunch of starving people, and starving people are not happy people. Happy people cause revolutions and stuff. So anyway, you never know what's coming. All right. So let's move on. Classification of metamorphic rock. Well, there's several ways. One big way we classify is the rock. Oh wait, this is where we're going to stop, wasn't it? Okay. Let me call roll again, and we'll move to the 261. Okay. All right, let's move there first, and then I'll call roll, because it'll be easier that way. Okay. It's going to take me just a little while to read it. If you're finished with it, I can take it. Yeah. Okay. All right. Okay. Yeah, we have. Okay, we have. All right, everybody, folks who came in late, I want you to hear it. We are going to put Sanford's Planetarium on Thursday. We're leaving the building. I'm going to try to get a vehicle for us. Leaving the building at 12:30. If you're going to be after 12:30, you can drive to Sanford or somehow get there. Yes.
Does it cost anything to do that?
No, it does not. It's absolutely free. Have you finished the observations?
I have finished that.
You did the observation part? That's what you're supposed to be starting now. These three. You may have done all this, but you haven't done all this. That hasn't been done yet. That you got done. I would finish it. Otherwise, you're going to have lots of your points. No one's turned that in yet, so don't, you rush. No, because you got to do the observations first. Okay. Oh, fantastic. Thank you so much. Okay, I thought you were picking me apart there. Okay. All right. I'm going to pause this, and we'll get over into... All right. What we're talking about is classification of metamorphic rock. Okay? And we won't do many of these. Shelby's here. Okay? But we'll do one major classification. And trying to find where we are. Yes, this is still on page 449. I flipped the page a little too soon. One of the major classification schemes for metamorphic rock is the degree of foliation. What in the world is foliation? Gals, y'all probably have a better handle on this than the guys. Any of you ever exfoliate? What you do?
It's like I don't know, it's more like a massaging and
Yeah.
Like you
What?
scrub off
Say,
the skin.
yes, you're getting off a layer of broken or maybe slightly damaged skin. Okay, exfoliate. In other words, you're getting off the outer layers of layers. Okay. Here is the key. Foliation. Have any of you ever heard of a portfolio? What does that mean?
Folder of all your work.
Okay, this is Tower, right? Okay. A folder of all your work. Usually that's in pages, sheets, right? That's what we mean by foliation. Okay? Foliage on the trees. We don't have any now because it's wintertime. But those are the layers, the leaves, layers, leaves, foliation. So foliation is the alignment of flat crystals, crystal flakes, into sheets. That's foliation. Okay? It's caused by all that pressure on the parent rock, which force things into sheets. Okay? They may have been three-dimensional. You're almost forcing them into two dimensions. Not quite, but close. The rock cleaves, I might be bothering everybody up and down the hall. It's called some distinct glares of unappreciative glares, okay? Caused by the pressure of the parent rock that's underneath it, pressure on the parent rocks. The rock cleaves along planes between the aligned grains, okay? Ooh. Remember our shale? The reason they can do a shale is that really foliates nicely. The sheets, in between the sheets, is easy to do. Cut them in that and then get them all about the same thickness. You can go to town with it. Okay? Now, other metamorphic rocks are non-foliated. The parent rocks consist mainly of one mineral and it doesn't compress into sheets. The grains are not aligned into sheets. So they stay three-dimensional. So there's no foliation there. So you either have foliation or non-foliated. Well, they can do better than that, can't they? Here's the classification scheme for metamorphic rocks. Non-foliated, that quartzite, for three-dimensional crystals, those tetrahedral structures, you're not going to foliate those ever at all. Neither will you do the marble. Marble is non-foliated. I just put it in the lab. There's no sheeting involved with that. You can have very fine foliated slate. We just talked about that. Easy to break those into very thin sheets. Finely foliated, that would be your schist. Be sure you get your letters right there, okay? Never mind. Okay, that's your schist. And then the coarsely foliated is the gneiss. Not very nice. No, remember that's the one that could be all warped and things, so it's not very finely foliated at all. Very coarsely foliated, nice. Still, you can see the layers, but they're not as easy to separate. Okay? So the extra metamorphosis, the pressure and temperature go from finely foliated to very finely foliated, very coarsely, and then quartzite, marble. Not at all. So that's one, and probably the major way we classify metamorphic rock. Okay. Told you you'd see that again. Okay. They love that, and it's a really good illustration of your metamorphic process. Shale is what kind of stone? Rock? Sedimentary. What kind of sedimentary? Again? You might be saying, I can't hear it. No, the limestone's chemical. Shale is your shale is mudstone or siltstone or claystone, really fine. And then it's foliated, somewhat, but we don't usually talk about it as sedimentary. All sedimentary rock come in layers except the chemical. Come on in, we'll accept you. Okay. Okay. Just got to find, there you are. Now, I guess we lost Brianna.
No, she's still.
She is, okay, I thought I'd seen her. But we did lose Carrie, or is she coming back? Anyone know? And I know we lost Tanisha because she said she had an interview. Okay? So, shale was clastic sedimentary rock metamorphosized into very finely foliated slate. It metamorphosized into finely foliated schist, and then it metamorphosized into coarsely foliated gneiss. And then if you add more heat to it, it's going to melt, and it goes back to granite, which is a igneous rock, and it's a intrusive, inside the earth, slow cooling, large crystal, coarse textured igneous rock. Light colored, low density, low iron content, igneous rock. Limestone, what was it? Second? Sedimentary, what kind of sedimentary? Chemical, excellent. Okay, it metamorphosized into marble, and here's a sample of marble. Now this has not been polished yet, but you see, if you think about the limestone you saw, it's pretty coarse feeling and seemed to be fairly porous. This is not. This is pretty dense stuff, and the crystals have been changed from what they were as a sedimentary rock, chemical sedimentary. If you continue heating marble, adding more pressure. Oh, I left this out. I meant to say it. There was something in between limestone and marble they don't talk about here, but builders and designers love it. It's travertine. The best I can figure out is a not quite fully metamorphosized marble. It still has some visible pore spaces in it, but makes a beautiful countertop. Looks like marble, but not quite the same, but very, very close, okay? But if you keep adding heat and temperature to marble, it actually will melt when it comes back as calcite. It says melted calcite. Yeah. Boy, that doesn't look like calcite. Yeah, it is. Just really lousy, really funny. And that actually goes back into those beautiful crystals that some of them you picked up. That's all. Okay. What's the next one? Sandstone. What kind of rock is that? Sedimentary. What kind of sedimentary? Clastic. Obviously, sand particles. And when it metamorphosizes into heat and pressure, it becomes quartzite, which is now changes the crystal structure of sandstone. You really have a lot of heat and pressure, and you get quartzite. And what happens if you add more heat to it? It melts and goes back to quartz. If it re-solidifies, that's an igneous rock. Now you can actually have, and we went through that again, that was recent. The igneous rock, fine grain, could be metamorphosized into schist, into gneiss, and then into granite again. And I meant to look, I didn't have to look up it on the right pages then. Let's go back to earlier in the chapter and find that coarse grain, low iron content, igneous rock. I know the name, I just cannot think of it. It's on that table. There it is. Rhyolite. Fine grain, low iron content, igneous rock, rhyolite. Okay, let's say that that's what we started with. Metamorphosized into schist, into gneiss, And by the way, this is that picture of the gneiss. Can you see why that would be coarsely foliated? Can you picture trying to separate those layers? The layers are there, but it's very coarsely foliated, okay? And this could be the result. I think that's the result more of your shale, slate, schist, gneiss. That's this gneiss, because the rhyolite, when it becomes a schist and then a gneiss, it's not going to have that distinct color pattern, I don't think. If it does, it's a surprise to me. I don't see chemically how that would be. All right. Second question. Okay. All right. You've heard of bicycles and tricycles. This is rock cycle. No, rock cycle. What are we talking about with that? That all rock are transformed into new types of rock by the Earth's interior and exterior dynamical. What does that mean? Dynamical. What do you almost see there? Dynamite. Okay, changes things. Okay, changing processes. Okay, what are some of these interior and exterior changing processes? Moving continents. Wait a minute, continents can't move, can they? A couple chapters from now, in fact, maybe next chapter, is going to be, yes, plate tectonics. Yes, we're moving, okay? Not very far, but moving. Not very fast, but we're moving. The moving, shifting plates, lots of heat, temperature, pressure going on when that's happening. So those rocks are being transformed inside and outside when those plates are shifting. Seas advance and seas retreat. Okay? Any not know where the Great Salt Lake is? Utah. Very good. Salt Lake City. Is that the capital of Utah? Maybe not be capital. Biggest city in Utah. Okay? Now, where is Utah? Near the coast somewhere? Nowhere near the coast. You got California, Washington, Oregon, and California. Then you got Idaho and Montana, and something. You got to go a ways before you get to Utah. It's in the middle of the mountains. How did you get a salt lake in the middle of a mountain? Yeah, at one time that was underwater, that was ocean water, seawater, salt water, and then the moving plates, moving continents, grew some mountains there. We call them the Rocky Mountains. They grew there as the pressure of those moving plates and trapped some of that salt water, and it never has all evaporated away. Now that's a guess of how it happened, but that's probably true. You have in Idaho and Montana basalts, which are on the bottom of the ocean. They got uplifted too. So yeah, we have, it's a really slowly changing planet, but we're always changing. Okay? Seas advance, seas retreat. Right now we've got global warming, seas are advancing. Okay. Actually, they say Miami Beach, some of the oceanfront property, is now ocean property. Okay. Its streets are going underwater there. Not that they're sinking, water's rising. We were in Venice. My wife and I were in Venice a couple of times. She had meetings over there, and I got to tag along. They don't have streets; they have canals. Okay, and some of the houses that are built there, their basements are now swimming pools. Okay, because their water is rising, the houses are staying right where they were. Okay, they're not really swimming pools, but they're underwater. They had to move up before. Okay, weathered and eroded. The rocks are transformed by weathering and erosion, by wind, by rain. 2 chapters from now, we'll be talking about that. Everything's changing. Slowly, but it's changing. Okay? Pressure, temperature, movement, interior, exterior, is happening. This, I think, is one of the neatest illustrations, and they did a really good job with it. By the way, I think we already hit this. All rock was at one time what kind of rock? Igneous rock. All of it came from molten material. Because guess how we started? A protoplanet. Molten piece of junk shot out from the sun when it was in its forming process, or something like that. All rock was at one time igneous rock. Well, what happens with weather and erosion? That granite, that other kind of rock, either water, high temperatures, actually plant materials, other things eat away at that. Chemical weather, we'll talk about that in 2 chapters. Weather and eroded becomes sand, silt, clay, gravel, whatever. Igneous rock breaks down, and becomes those pieces that come out of that, or the solutions that come out of that, then sediment. The particle solutions become clastic sediments. The chemical solutions become chemical sediments. So you have sedimentary rock. Well, the lithification, remember that? 2 steps in lithification? Texas 2-step. Compaction then? Cementation, exactly. The 2 parts of that happens to the sediments. You have sedimentary rock. So you start with the sediments. It settles out. Lithification makes it into sedimentary rock. Now guess what happens to the sedimentary rock? Some of it erodes away, okay? Like that sandstone we had in there, you rub on it and it becomes sand again. So it becomes sediment again and starts back into a short loop there. But other of this sedimentary rock, other rock get on top of it, on top of it, on top of it, more temperature, more pressure, it changes it to metamorphic rock. Give me an example of a sedimentary rock going to metamorphic rock. Anyone? We hit several. Shale going to? Well, shale, yeah, going to the roof. Slate. Slate, okay. Shale going to shale with sedimentary rock. Very fine clastic rock, silts or clays, it became slate. Okay? Some of this metamorphic rock, weathering, erosion, makes it back into sediments again, starts its cycle over again. But some of this igneous rock has pressure on it too, gets buried, temperature, pressure, it becomes metamorphic rock. Remember that fine-grained igneous rock could become schist, just like the shale became schist, okay? And then gneiss, and then whatever, okay? So you go through this. If you add more heat and pressure to that metamorphic rock at some point, it's going to melt. Becomes magma again. Magma again. No, that was just magma. And then it cools and hardens and becomes igneous rock. We're back to igneous again. That's probably my phone. Okay. Let it ring. All right. That's the rock cycle. You thought I was going to start singing rock music. Never mind. Ha! Here she is. Okay. We got everybody back except Carrie and Tanisha. Hard K sounds. Okay. There is a blurb here, top of page 450. I'll let one of you read his name. Well, I can say his last name. Goldschmidt, Victor Goldschmidt, Swiss-born, but went to Norway, Norwegian chemist, who has been called the founder of modern geochemistry. Certainly would be a potential paper topic. However, this stuff here can give you ideas. You need to get materials outside the book. So this is not your source. This could be your source of ideas, but need to go for it. Get it elsewhere. Okay? Several other people are mentioned. William and Lawrence Bragg, Max von Lollies, you can read on that. A lot of that is not talking so much about geology, but other sciences that involve. But if you tie them together well, that would work. okay? There's a real pretty picture of a banded metamorphic rock, very, very old. That was the one we saw at the beginning of the chapter, and then more recently. Marble is I think we saw this picture, coarse grain metamorphic rock. Interlocking calcite crystals because of the pressure and temperature change that crystal structure. And I think that's the last one. Let me see. Yep, that's it for this chapter. Okay. Now, guess what I'm going to say next? Nothing replaces reading the chapter. Please read the chapter. We've just hit the high points. The slide set only shows little things about it. Nice features they can show slides. Please read the chapter. And after you do, the summary is a little bit shorter than some of the summaries, maybe about average. It hits the high points again. Key terms, probably about an average list here, not as long as some. It's alphabetically, but they list the page numbers so you can find it easily where it's first defined or explained. But then the applying the concepts. 43 questions, maybe a little on the light side there, but still quite a few. Multiple choice questions. If you can answer those correctly, you've got a good jump on getting the concepts of this chapter together. Okay? The answers are given here. If you don't know why this is the correct answer, or you think it may be wrong, bring it to class. We'll talk it through. Questions for thought, 19 in this chapter. That's quite a few, more than average, I would say. Read through those, think through those, see if you understand what they're asking for. Use all the other materials. For further analysis, only 4 of those, not as many as you'll have often. Parallel exercises, again, you have these in your books. If you have the little thin book, they don't have the answers. If you have the bigger books, the Group A parallel exercises have answers in the back. Any questions? Chapter 17. Okay. All right, we're ready then. Now, that means what's going to happen Thursday? We meet, in the room, that we were just in at 12:30. The van leaves. I'm going to try to get a van. I don't have it yet, but the van leaves at 12:30. We need to be there at 1:15 or as soon after that as we can get there. So if you're not here at 12:30, you're going to have to bum a ride, drive yourself, hitch a ride, walk, thumb, whatever. You got to get there as soon after 1:15 as you can. Okay? Try to be here at 12:30 or there at 12:30, and we'll leave as a group. Okay? If it's more convenient for you to come from home, come from home. That will be perfectly fine. Be at Sanford, the planetarium, at 12:30. Now, I went over this earlier. I can make copies if you need this, but you know where Sanford is? Lakeshore Highway? Okay. You know there's at least 2 and maybe 3 entrances. One is called Montague Alley. It's an entry off Lakeshore, off of 65, but don't take that first one. I think the football field is right down in that area. Don't take that one. Go on up till you get the main entrance. The main entrance is the one with a light. This one may have a light. This one has a light, big gates, fancy entrance, separated entrance. The entrance here, the exit there, gate in between, green area in between. That's the one you take. Okay? Come up, turn in there, take a left there. The first, and it used to be a stop sign, I don't think it is anymore. The first crossing street there is Montague Drive. Whether you see the name or not, that's what it is. Hang a right. Don't go up the hill toward the big, pretty library at the top. Okay? Take that right first. Now, there is a road that turns off of that. Don't turn there. Stay on Montague, but it's going to make a gradual left, and you basically make a 90-degree turn, but it's a very slow 90-degree curve. You finally get up here, and right by what they call the conservatory, there will be a stop sign there that's a pedestrian crosswalk. Stop, okay, but don't stop for good. Let the people pass. Then you go on a little bit further, and you can even see that next stop sign. That's the stop sign where the planetarium is. However, you don't park there on the street. There is a parking lot just beyond that, okay? That's not many places down there, and at 1:15 in the afternoon, probably they're all going to be filled. But if you see one down there, it's okay to park there. If you don't see any down there, don't waste your time. Keep on going up the hill, and here when you get, it's still within sight, but it's a good little ways up here, you'll see a surface parking area here to the right and a parking deck to the left. If you turn in here, you can park in the surface area, much more parking under the deck. I've never failed to find a parking place in there. I've seen it this full and this one full, but I've never seen that one full. So the odds are that's where we're going to wind up. If by chance it is full under the deck, go back out and continue just a little bit further and then park on top of the deck. You can get to the top part if you go further up. This is going up a hill, so you go in the lower part from the lower side. One of those others, you can find a place there, or wait till someone leaves. They're always leaving in between classes. So I think you'll find the parking place there. That's why the more of us are in the van, the better. We don't have as many cars there, okay? Then you have to walk back down the hill and right by that stop sign, go to the outside of the loop, and you'll go down a few steps and take your first left. That's where the planetarium is, okay? Now, you'll be coming in off the parking area, and you'll be, I don't know how to do it, but somehow that's the entrance down there. Because the other entrance has steps, that one doesn't. Okay. All right.
So what's the building called that we gotta go into? You know?
It's called the Christenberry Planetarium. The trouble is, it's not labeled very well. There's a little bitty sign on it that says that. But it's just past, you'll see a bunch of greenhouses and other things here, a big building here, and this one comes up to the street. It's the end of that building. It looks like it is all connected there, but it's that end right at that second stoplight. The stop sign, not a stoplight, stop sign. Okay, one stop sign here, the second one there, that's the one you go to. But you've got to park first unless you get someone to drop you off. And but once you get there, you go down a few steps, hang a left, you're right there at the planetarium. It's not, you go in, you'll see pretty pictures and stuff, you just keep going in, it gets darker and darker, and then there's a place to go. And my guess is you'll probably come in the very lowest level down there, but you can see everything from there. Yeah. And you'll like Mr. Weigel. He has stories out the ears. Young guy, really excited about what he does. If anyone needs a copy of this, I can make copies. Let me know and I'll do so. Okay, then let's move on to plate tectonics. All right. Oh, I was finishing what I said. We go to the planetarium, we meet here, we leave for the planetarium. That's going to be somewhere between an hour and 2 hour show. So that's going to get us through probably around 2 o'clock or so. No, you're dreaming. Slap yourself. He fell asleep. He's dreaming. Wake him up. Okay. Now, no, 1:15 to 2:15. So 2:30 to 3 or so will be at the planetarium on our way back somewhere here. We get back here. We have time for our test. If we have time before 4:30, we'll continue in chapter, whatever this is, 18? Yeah, 18. So that's how it's going to go. Yeah. Oh, I thought you had a question. So we'll meet there, leave for the planetarium, and finish at planetarium. We got to come back. All those in the van anyway are going to be back. The rest of you come on back if you can, if it's convenient. If it's not, that's okay. And we'll meet again, finish up, or continue in chapter 18. And then when 4:30 gets here, we'll stop and have the test on chapter 17. Okay? If you can't make that, you'll have to make that up sometime later. Okay. Let's see if I can get it. That time it worked. Okay. So let's move on to chapter 18. What's that? Can you what? Oh, absolutely. I'm burning up in here. Okay. Now, maybe, it's nicer outside than this. If I had projection, we'd go outside. Okay. Now, so let's get started on chapter 18. I thought it was already starting, but it hasn't. It's taking its sweet time. Here it is. We are recording, so let's go from current slide. So, plate tectonics. What do we mean by that? Well, here's sort of one definition. The Earth has an internal structure and cycles materials between the surface and the interior. It's always happening, folks. Always. Okay? That's the core concept of the chapter. Now, in the book, that's on page 457 or somewhere thereabouts. White print on a yellow background, not really clear. This is much clearer. Now, we'll see this picture later, but let's just take note of it while we're here. Here we are. This is North America. This is U.S. right in here. There's Florida. We're right here. Okay? We're part of a big plate called the North American Plate. It goes down, includes most of, not all of Mexico, but most of it. A little bit of, I guess that's Cuba. That's a pretty lousy picture of it. It goes halfway across the Atlantic Ocean. We'll talk about that a little bit later. And includes Greenland, Canada, Alaska, the Aleutian Islands, and actually the end of Siberia. Now, I don't know where it actually ends over here, but actually it almost makes it as far as Japan. This is the Japanese islands here. So it's a pretty good sized plate. Now there's some smaller plates around it. The Caribbean plate here, which is most of the Caribbean Ocean, not all of it, but a lot of it. There is a little bit of Central America, Panama, for instance, and some of those neighboring countries in it. A little bit of South America in it, and a little bit of Pacific Basin in it too. All right. Another small plate that's nearby is the Nazca plate. Okay. Not going to do a lot with that, but that's largely responsible. The colliding of the South American plate with the Nazca plate. The Nazca plate, we'll talk about later, goes under the South American plate here, and that's resulted in the Andes mountain range here. Okay? Now, there's a big plate out here, the Pacific plate. And in between, and actually part of, you see, this is, I don't know if you're familiar with it, it's the Baja Peninsula, south of California. It's in Mexico. That's actually in the Pacific plate. It's that Gulf of California that's here, that's in Mexico. That's the boundary, okay, of the thing. Well, there's a little boundary here, up here too. Part of California is Pacific plate. That Pacific plate and the North American plate, where they meet, is the San Andreas Fault. Have you ever heard of that? That's what's caused most of the earthquakes in California along that plate. Los Angeles is down here, San Francisco's up here. Part of that, the coast there, is in the Pacific plate. And then there's a little bitty, I think this has to be the smallest plate ever, is the Juan de Fuca plate. There's a few islands up there. I'm trying to think of what they call those islands. I think it's the San Juan Islands. I think that's what it's called. That are up there, and they are basically about all there is of the Juan de Fuca plate. Okay. The Philippine Island group and a lot of the South China Sea, they're all in the Philippine plate. The Eurasian plate is a huge plate. Huge plate. Most of Asia is in it, and just about all of Europe is in it. The Eurasian plate, huge piece of plate. Not all of Asia. India is largely in the Indian-Australian plate. Australia's in that, India's in that, and a lot of the Indian Ocean and some of what we call the Pacific Ocean. You know, there's all sorts of island chains out here. New Zealand, for instance, is over here, right down here. That's part of the boundary of that. And there's other island chains in here too. We'll talk about that later. At the bottom of the globe is the Antarctic plate, okay? Pretty good sized plate, but it looks much bigger here because, you know, you can't take a sphere and draw it on a sheet of paper without expanding the top and the bottom way beyond what they should be, okay? And then there's the African plate. And in between that is the Arabian plate up here, and then the African plate here. Mediterranean Sea is sort of the boundary there. And you get back into this and you pick up again there. They don't name this one. There is a little plate down here, but they don't have a name for it. I'm sure there is one, I just don't know it. This is the South American plate, which again is about half of the Atlantic Ocean and everywhere over until it bumps into the Nazca plate or the Antarctic plate down here. Okay? And then this is the end of the Eurasian plate here, end of the African plate there. All right. We're made up of pieces of the jigsaw puzzle, basically. Okay? Now, they don't fit all that nicely. They rub against each other, and they give us problems. So that's what this chapter is about. We're made up of this internal structure. We cycle material between the surface, interior, and interior back to the surface. They didn't say the last part, but it's there too. We'll talk about that, though, in a subsequent chapter. So what is the history of the Earth's interior? We feel like the Earth was formed about 4 billion years ago, 4.6 billion years ago, as part of the solar nebula. Boy, that's a little bit different. Well, what do we think the sun's age is? Around 5 billion years, and we think it has about 5 billion left to go to make a total lifespan of 10 billion. So we were formed in the early process of the sun blowing up and coming together and doing all its mess. It sent the planets out there, and the planetary nebula are the protoplanets, you know, stuff like that, circling the sun. So we were formed about the same time the sun was. It may have taken time for us to cool. That may have been part of that 400 million years, you know, short time, you know, to cool. It took us a while. We were pretty hot-headed back then. So anyway, we cooled and became the Earth. The early Earth, and we talked about this, I think, before too, had a molten surface. The surface of the Earth was all melted rock, basically. Okay? Where did that come from? From all the activity of the solar nebula, all the explosions, the radioactivity, the bombarding with other stuff that was getting kicked out of the sun. It was just a mess. And all those collisions made for a molten surface of the Earth. The surface cooled and crystallized into igneous rocks. All rock were at one time igneous rock. We started as a molten ball of magma and lava, and we cooled to become igneous rock. Now, the heat that accumulated from the radioactive decay materials and all the other stuff going on led to a second melting. This time it's the interior, because all this pressure from the exterior, as it cooled and condensed a little bit, added more pressure to the interior. The heat got trapped in there. So that melted the interior of the Earth. Okay? The melting occurred in pockets, not throughout the interior. Okay? And that has allowed for a sort of a strange mix. As you go down, you run into all sorts of different things. Well, different things, differentiation. The melting and the gravitational settling of the heavier elements. Most of the heavier elements went down. The lighter elements stayed near the surface. So what do we have mostly on the surface? Our light-colored igneous rock. They made their way up. They cooled slowly, large crystal size, coarse grain, but they cooled slowly as they were melting. But they went up the irons went down, basically. But there's differentiation. There's all sorts of variation in that. They gave the Earth its present stratified structure. The crust, remember, was largely siliceous material, silicon, oxygen, iron, the lighter weight metals. The iron is not light, it's just there was so much iron here. And then as you go deeper and deeper, you get more and more iron, nickel. For some reason, magnesium goes down there too, okay? But that's what gave the Earth its present stratified structure. The outer core of the Earth is still molten. So you have the crust, and then we have the outer, well, leaving off the part. We'll get to that in a minute. You also get what they call the mantle. We haven't mentioned that yet. We're going to get there. But then the outer core of the Earth is still molten, still melted. Mostly iron, okay? If we could just tap into that, we'd have all the iron we ever needed. I don't think we want to tap into that. Tap into that, here comes all that molten iron right out the tap, You have a big volcano on your hands, so we may not really want that, okay? Conditions at the Earth's center, by the time you get down there, the pressure is so great. It's about 3.5 million atmospheres of pressure. How many atmospheres of pressure do we have on us right now? 1. The weight of the atmosphere, that's 14.7 approximately pounds per square inch. A square inch is about your two thumbs together. That may be a little too big, but about like that. Okay? That's a square inch. Every square inch of our body has 14.7 pounds of pressure from our atmosphere on us. We talked about this before, right? Okay. We've got pressure inside us pushing back out, so we're at equilibrium. Actually, a little more pressure inside than out. That's why when you cut yourself, the blood comes out, it doesn't go in. Okay. So, but now that's 1 atmosphere. Go down 10 meters in water, that's about 30 feet, about the height of this part of the building from the parking lot level there, first floor, second floor. This part has a 3rd floor. That whole depth, if you were underwater that deep, you'd have another atmosphere of pressure on top of it. Okay? Then another 10 meters down, another and another. That's underwater. You start going under rock, you don't have to go as deep because rock is much denser than water, so you get another, and you don't have to go very far at all. Somewhere down there, 3.5 million atmospheres of pressure, we don't want to go there, okay? Temperature, 6,000 degrees Celsius. That would be, I'd say close to 10,000 Fahrenheit, degrees Fahrenheit. Okay? That would be Kelvin at another 26, 200 some hot. Still more than 6,000. Okay. Awfully hot. Incredible pressure. That makes the inner part of the core, at that kind of pressure, it goes back solid again. Awfully hot solid, but it just doesn't have enough room to move around to be a liquid. The outer core, that is a liquid. Then we have the mantle. So, what is the evidence we have that supports that thing? Has anyone ever drilled down there and taken core samples? Nowhere close. When we drill down and take cores, we're just scratching the surface of the crust. We're not even getting into the mantle most of the time. And surely not getting into either core, okay? So how do we determine, what evidence gives us that that was indeed a true picture? Well, first is the Earth's magnetic field. Does anyone know what creates a magnetic field? Moving charges. Have you ever heard of an electromagnet? Yeah. You get a charge, a direct DC current going in a coil, maybe with an iron core in the middle of it. It becomes a stronger magnet than any magnet you can find. It's not electromagnet. It's way stronger. So a moving charge induces a magnetic field. Okay? Well, why would we have a magnetic field? We're just spheres spinning around there. Well, there must be something, charges being knocked off somewhere. The best way to describe that is a outer part that's solid, an inner part that's liquid, and that's knocking charges around and making them spin with the spinning of the Earth. Guess what? That creates a magnetic field. Can't think of any other way to create as strong a magnetic field as we have. Now, gravity effects. If you had had the first half of the book, which just assumes you have, this would make more sense. We haven't. Most of you have not had the Physical Science 112. So therefore, that's why we skip a lot of the examples, because they're counting on that. But the gravity effects, I'll go and write it down for you. The universal law of gravitation follows like this. The force due to gravity, let me get my pen color there, okay. All right, the force due to gravity is equal to this constant, G, universal gravitational constant, m1 times m2 divided by r squared, where r is the distance from the center, okay? Now, talk about the gravitational effect of the Earth. Basically, this is between two bodies, so just of the Earth, just take one of those m's, okay? Now, in order to account for the gravitational field that the Earth has, you know its radius, you know approximately its mass, you know that constant that's been determined. The only way you can get that mass to be that massive is if the densities are increasing greatly as you go down. And so these things added up with the gravitation, the electromagnetic field, the magnetic field, yeah, you can't really model it much any other way. The gravitational effects are some of the things. Heat flow. We have a good guess on the temperature down there because we know the heat of most of the magma that we detect when volcanic eruptions and stuff. We have a good idea of how hot that is, what it has to go through and stuff like this. The heat flow also models that. Now, this is the big one though, and this is really interesting. Vibrations in the Earth. Does the Earth vibrate? That's what an earthquake is, the vibration of the Earth, okay? And that's the waves that are created by that are called seismic waves. That means waves coming from earthquakes, basically. Though you do get seismic waves from atomic explosions, that's how nobody can get away with an atomic test without the whole world knowing about it. Because atomic explosion is big enough to create seismic waves. And if we haven't heard of any earthquakes there and yet detect the waves and we see it's in North Korea, guess what? We know they had another nuclear test or anywhere else in the world. And we usually notify people, so when you see it, they won't think there's an earthquake somewhere. Okay, now, these vibrations radiate outward from earthquakes. Those are your seismic waves. They're also noted from the nuclear explosion. I didn't realize that was on here. Okay. Now that leaves a little bit, yeah, these are all the pieces of evidence, but it doesn't really tell you how they're put together. Now your book will explain a little bit more, but not enough until we go to the next slide. Let's look at these seismic waves. There are three types of seismic waves. The first is called the P wave. Any idea what the P could stand for in P, prime, P waves? Second? I couldn't hear. Okay. Actually, it's primary. First. The first wave is the primary wave. There's another good definition for it. Pressure wave. It's a pressure wave. These are the fastest wave. Now, why do we call them pressure wave? Okay, an example of a pressure wave, not the fastest, but would be when I'm talking to you. Hopefully you're hearing me. Do you hear me now? Okay. Okay? If you held your hand in front of your mouth when you're speaking, what do you feel? Little air pressure things hitting your hand. Okay? That's a pressure wave. It goes in the same direction that the disturbance goes. It's a primary wave. It's your fastest wave. Pressure waves, P waves, move through rocks, in other words, solids. They also move through liquids, solid and liquid material. Primary waves, pressure waves go through. If you've ever been in the bottom of a pool, you know you can hear in the bottom of the pool. In fact, it's pretty clear hearing too, okay? So solids, liquids, gases all experience pressure, compressions, and pressure waves. Now, solids, sounds travel faster through solids than through liquids or gases. You believe that? Have you ever watched the old cowboy and Indian movies? How did the Indians know when the trains were coming? Or the robbers know when they put their ears down on the track. The sound goes through the metal much faster than it comes through the air. They can hear the train way further away than they could just listening for the toot of the horn. Not going to go as fast through. So they go through solids and liquids and at different temperatures. Now, there's an S wave. Guess what the S stands for? Secondary wave. There's another way, a shear wave. Now, what do we mean by a shear wave? A primary wave, the pulse is in the same direction of the promulgation. I'm talking, and the wave, the pressure waves goes like this, and they go to your ears, right? Same direction. A shear wave, ever when you were a little kid, I know I did it, and your mom or dad had the hose drug out across the yard to do something. They hadn't turned on the water yet, and you pick up the hose and do that to it. Okay? What happens? It goes down the wave, down the hose, right? Your motion was up and down, but the wave goes in that direction. That's a shear. Going this way with the action, but the wave goes that way. Compressional wave, the action is in the same direction as promulgation. So that's why it's called a transverse or shear wave. Not as fast because action's going in a different direction. So it's not as fast as the primary waves. So there's a key. P waves travel faster than S waves. That's important later. It's always important, but we'll know why later. Here's the other thing, though. A shear wave will not travel through a liquid. No way. Pressure will travel through a liquid, but contrary motion, counter motion, yes.
Isn't that the one they use to measure how big the earthquake is?
What's that?
Isn't that the one they use to measure how big the earthquake is?
Okay, they're used to measure how far away. Okay, and they are used in a sense to measure how big because the magnitude of both of those waves has to do with how big the earthquake was, but also how far it goes and stuff. You can do it. Lots of things contribute to that. But yeah, that's a big part of it. The magnitude of that wave, yeah, that's how big it is. Okay. Now, these S waves don't travel through liquids. That's going to give us a big clue of the structure of the Earth. Believe it or not, that fact that seems unrelated to anything about the Earth, that's still going to give us. Okay? The third types of seismic waves are your up and down or crest and trough waves. Those are surface waves. After it reaches the surface, that's what you get. Water waves or surface waves, or up and down trough, crest and trough surface waves, much like water waves. Air and other things get it. If you've ever seen a picture of a nuclear test, an atomic test, you'll see dust move out just like water waves. Okay? You'll see those rings just heading outward. Okay? They're pretty strong too. Okay? Wipe out things as they go. But that's your surface waves, like a water wave, but it doesn't have to be water. It's the slowest of all those. Okay? Now, that's where the primary wave or the secondary waves reach the surface and then they move outward. Okay? Pressure waves keep going. Secondary waves or transverse shear waves can't go through If they can't go through a liquid, they're not going through a gas either. Think of liquids and gases as fluids. They can't go through fluids. Okay. Now, here's a picture. I forgot about this. The pressure wave is like a spring wave. Do that to a spring and you'll see, you do that, but then you'll see that, what they call condensation, where it gets close together, move down the spring until it reaches the end. Now, actually, if this is fixed here, you'll then see it bounce off and move back the other way. Pretty interesting to see, but that's the pressure wave. The particle motion is in the same direction as the wave propagation. Primary pressure wave, fastest waves. Your secondary waves, your S waves, your shear waves, transverse waves, the particle motion is up and down, but the wave propagation is down. And you'll actually see it reach here, and if that's allowed to go up and down, you pretty much lose it, but if that's fixed, you'll see the wave invert and go back. That's physics, we're not going to get into that now. But that's the difference. Primary wave, pressure waves in the same direction. Secondary wave, shear wave, transverse wave is in this is also longitudinal wave here too. Need to recognize all three of those words. Okay. Now, how does that contribute to our understanding of the Earth's internal structure? Okay? Oh wait, sorry. They're going to get to that later, sorry. Let's look at the three main zones. I don't like the way this chapter is organized. It's okay, but you know, it seems like they could have done a better job of it. But right now we're on page 459 approximately. Okay? So three main zones. It's going back to the structure of the Earth now. Look. Seems like we've got away from that. We have the crust, which is the outer thin shell. If you could fit the globe of the Earth in here, the crust would probably be about like that. If you get the whole Earth in this room, the crust would be about like that. I mean, it is awfully, awfully thin. We live in the crust. Most of everything we do is in the crust. Now, the mantle is much thicker than the crust. That is an understatement. Much thicker than the crust. If this was the crust, the mantle is like this. I mean, huge compared to the crust. And then the core, that's the central part. Okay? Now, get this. The crust, there's not much of it. Covers a large area, but it's also the lightest weight material, so it's not very dense. Dense enough, but not very dense. Mantle, because you got pressure of the crust coming down on it, and the water and everything else, it's a little denser. The core, the liquid part, is really dense, but the inner core, the solid part, is extraordinarily dense. There's the core. Let's see if we can see a picture of it, or an illustration of it. Okay, the crust is this thin little brown region here. Okay, really, really thin. The mantle is this, it's the bulk of the Earth, really. Okay? Now, this part is probably closer to true. There's not a clear boundary here. It's a rugged boundary. You know, it's not smooth. I don't know. I mean, no one knows for sure, but it's doubtful that it's smooth. It sort of smears into each other here. But this part here, that's the mantle. Now, a little bit later in this chapter, we're going to break the mantle into pieces. Upper mantle and lower mantle. Okay? It's already done for us. We'll talk about some more refined structure later. For now, we're just talking about the mantle. Then we have the outer core, which is liquid, molten rock, and then the inner core, which is at such enormous pressures, it's going back and being a solid again. Extraordinarily high temperatures, but it's just too pressed together to melt. Okay? So that's your gross anatomy of the planet. Okay? The thin outer crust, big thick mantle, outer core, which is liquid, inner core, which is solid. Now, most of the planets are sort of like this. And remember, Jupiter, however it was, when you got to that inner core, that was several times bigger than the Earth. What, 13 Earths could fit in their inner core, and then you had all that outside of it. So Jupiter is huge. Okay. So let's look first at the crust. covers the entire Earth. All of the Earth is covered by the crust. The mantle doesn't break through anywhere. Okay? But there's two crusts. There's part of the crust that's called the continental crust. Well, let's start with the oceanic crust. That's underneath the oceans, underneath the water. That is the oceanic crust. Two characteristics of it. Much thinner and a different type of rock. Basaltic rock. That black rock that we saw, if you looked at it in the thing, we'll be dealing with it in a later chapter 2. It's much denser than the crust. It's much denser than the continental. I mean, it is part of the crust, but it's much denser than the continental crust. The continental crust is not dark basaltic high iron content rock. It's high silica rock with much more silica in it, so it's lighter color, lower density, lighter in density too. That's the continental. But not only that, they left off something much thicker. The oceanic crust, much denser, but thinner. The continental crust, much thicker, but less dense. Okay. It's granitic rock, meaning low iron content, basaltic rock, high iron content. Now, the other difference between these two, granite rock is large crystal size, coarse grain, it cooled more slowly. Basaltic rock cooled quickly, small, fine grains. Small crystal size, fine grain. Why? Because most of it was formed by hitting the ocean temperature, ocean to cool really quickly. So therefore, it's very fine grain. Now, in between the crust and the mantle, and I don't even know how to pronounce that. I say Mohorovicic. I think that's how, it's close to how you say it. I know usually when you see the CIC at the end, that's given a seal. It was a CH sound. Mohorovicic. Generally, they call it the moho. So that'll be fine with me, the moho. That's the separation, the boundary between the crust and the mantle. They call it a discontinuity because things change really abruptly there. Your density changes, your composition changes, everything changes really significantly there. That's the mantle to crust boundary. Now, the seismic wave velocity increases sharply as you go from the crust to the mantle. That seems like a dumb statement to me, okay? Because the seismic waves usually start in the mantle and make their way to the crust. Now, I guess some shallow earthquakes could start in the crust and then go to the mantle. But I would think most of them, not really fair. We'll talk about that a little bit later. But I would have said decrease sharply when they go from mantle to crust. But I guess what they're talking about, and it could go either way, but it changes. That's the big deal, okay? Because the crust is much lower density, it doesn't transmit sound as rapidly. The mantle, higher density, it transmits sound much more quickly. So the wave velocity is greater, okay? Not just sound, it transmits all waves more rapidly. Okay. Here's sort of a pictorial guide to this, okay? Your continents are made of the continental crust. Tell me two characteristics of it. Say again? Granitic, meaning lighter density, and that's less dense. Also larger particle size, less iron. Okay, all that goes together, but thicker. You see that from the top one. The oceanic crust is thinner, that means the continental crust is thicker. Different materials, different thickness, different characteristics. Underneath the ocean zone, you have the oceanic crust. Now, don't think it's super thin. It's still thick, but not nearly as thick as this one. And it's mostly basaltic rock, much denser, okay? Mostly because of the iron content. very high iron content. Dark, this is lighter color, but also light density because it has less iron. Now, underneath both of those types of crust, you'll have the mantle. Now, it's generally way down there. But notice it's a very irregular boundary. And this is just an example. It's not a smooth boundary at all. Now, something's a little wrong with this picture. And we won't realize that until we get later in the chapter. Okay? Yes. They call me the Sandman. Okay. All right. Now, this is the Mohorovičić discontinuity between the crust and the mantle, whether it's oceanic crust or continental crust. Here's what's wrong with this picture. The oceanic crust typically does not crawl up the continental crust. It's denser. It usually subducts under it. You'll see this in later illustrations. Why they made this error here, I don't know. There's nothing to support having the crust climb up there that I can think of. It may happen some places, but generally it subducts under because it's denser. It goes underneath the continental crust. But the deal here, these are not smooth boundaries. They're very rough and rocky, jagged. So therefore it's not a smooth transition. Anything. The Mohorovičić, the moho, is not a smooth transition. Very rough, irregular transition. Boundary. All right, let's look at the mantle. Thick, thick, thick shell between the crust and the core. Takes up 80% of the Earth's volume. The crust, almost none. The mantle, 80%. Most of the Earth is built of the mantle. But it only accounts for 2/3, which is 67% of the Earth's mass. Why would that be true? How can it be 80% of the volume, but only 67% of the mass? What's left?
The core.
The core. And what do you guess about the core? All that pressure makes it denser, way denser. Okay? So therefore, even though it's only about 20% of the Earth's volume, it has a full third, 33% of the Earth's mass. See, we're not even counting the crust. I mean, it's so minuscule. Okay. The mantle is composed mainly of olivine. Remember that? Olivine? It was one of the ferromagnesium silicates. Okay? The key here is the silicate. It's not pure iron. It still has siliceous material, silicon dioxide in it, or silicate, which is silicon, SiO3 or O4, okay? I think it's SiO4. Still has that in it, but it's ferromagnesium, iron, and magnesium, and nickel compounds. That's what makes it denser, okay? Go even deeper into the core, I think it's mostly iron. You don't have many silicates down there. So it's still sort of a mix. The crust, lots of silicates. Non-ferromagnesium silicates. The mantle, largely ferromagnesium silicates, olivine being one of them. So, what are our data sources that support how much of it is mantle? How thick is it? You know, all this kind of stuff. Seismological data again. Now, we haven't defined how that's true. We're going to see that in the subsequent slide. I don't know if we'll get to it today or not, but that's it. Now, this next statement gives me the creeps, okay? What's the data source for how thick and how much and what's in the mantle? The nature of meteorites? They're coming from outer space. How can the nature of meteorites tell me what's in the mantle underneath the crust of the Earth? Yes? That is, we're all made out of the same leftover material. You're absolutely right. Okay? So, It's a weird way to look at it, but yeah, we can study the meteorite to know that's what was inside of us too, okay, the Earth meaning. And therefore, if they have large amounts of olivine in them, that's probably most of the mantle is made up of olivine. Now this is in connection with the other things as well. And then of course, we can get materials ejected by volcanoes, because guess where that's coming from? Generally the upper part of the mantle, or near the moho. Maybe a little bit into the crust too, but mostly from the mantle. So yeah, we can tell what was there. The thing is, it's melted and it's, a lot's going on since it left, so we can't tell a lot about it. Now, what they call the basalt correlation. Now, what was a basalt? Yeah, a dark, say again, bottom of the ocean. Fine grain, meaning the crystals form rapidly. That means small crystal size. They form rapidly, mostly under there, but we have basalts on the surface, but it probably used to be underwater, but okay. The basalt, these are close to the silicate chemical composition of the stony meteorites. So this is where those come. The basalt correlation and the stony meteorites, they're very, very similar. So the basalts, they're right above the mantle. Good idea, that's what the mantle is. Okay? That's where those correlations come from. And this is the most common volcanic rock is coming from the basalts. They cool quickly because they came from volcanoes and cool quickly. Small crystal size, fine grain basalts, largely iron content, probably iron silicates. Okay? Let's get into the core. You better have on some good clothing. Makes up about 15% of the Earth's volume. What does that leave us with for the crust? The mantle was 80%, the core is 15%, 5%. So by volume, the crust of the Earth is only 5%. And when you figure it's spread over the entire surface of the Earth, it's pretty little, pretty thin. Okay? But the core makes up 1/3 of the Earth's mass. What's left over mass-wise? Nothing! Because we had 2/3 in the mantle, 1/3 there. The crust is so light, it's less than 1%. You're absolutely right. It's there, but it's not very much mass. A decent volume, but it's pretty spongy, spread out, low density. So it has 5% of the Earth's volume, but less than 1% of the Earth's mass. Wow. So, what leads us to believe that you got a liquid core and then a solid core? The P-wave seismologic data. This is where we're going to tie these together. The primary waves, tell me something about primary waves.
They go through solid or liquid and gases.
They go through fluids and solids, exactly. Fluids being liquids and gases, solids being, but in the Earth we're only dealing with liquids. Don't worry about the atmosphere, okay? They travel fastest too, but they will go through it all. So, what do they mean by a shadow zone here? Here are the P waves, primary waves. You can measure, say, this is your earthquake here, okay? It could be in the lower part of the crust or the upper part of the mantle. Somewhere in there, there's where your earthquake is, okay? Now, the primary waves make their way all through here, but then there's a zone here they don't come. Lower part of the Earth, beneath, more than halfway around the Earth, you don't get any P waves at all, and then you pick them back up again here. What would account for that? Well, they've done all this modeling, and the only thing they can come with is by figuring in densities and whether it's solids, liquids, or whatnot. There must be, just the way things happen here, this must be very different in here than it is here. This is the mantle, this is the core. Now, To me, they got the core being too big, but we can let them live with that. But every time it crosses a boundary, it changes the wave nature. Crosses here and it changes back. The modeling of this would have us require this to be a denser core. Now that's all we can know now, a denser core, a significantly denser core. That's why you have the shadow zone. That's why you have the shadow zone. And the primary waves come on through here, but they don't come here because they either get deflected here. That tells us how far down it is before you get to the boundary between the mantle. In other words, how deep is the mantle? This tells us. This bending of the waves here and here, that tells us how thick the mantle is on average. Okay? And then that you have this shadow zone here, this tells you approximately the density of the core. So if you know the density and the volume, you can figure out how much mass is there. Okay? So this gives us a good model that there is a core, it's much denser than the mantle. There is a boundary there, that gives it to us. Just reading these waves. They'll do that almost, I mean, it's so bizarre that it's a very, very good estimation. Okay, the primary waves tell us that. They tell us the size and the density of the core. Okay. What do the S waves tell us though? The S waves, what does S stand for? Secondary. Another word? Shear. And another word that doesn't start with S? Transverse. Transverse. Primary was primary. What's the other P word? Pressure or compressional wave. And the other was longitudinal, moving in the same direction of the propagation. Here's what we get from our S waves. Now they draw these little squiggly, okay? Here's your quake, somewhere between, say, the lower part of the upper part of the mantle. There's where the earthquake occurs. And your S waves go out like this, and they get bent around the core just like the primary waves do, to just about the same angle, again confirming the core is about that size. But guess what? None of them come through. What does that tell you about the core? Part of it has to be liquid. Because if it was solid, S waves would come through too, but they don't. So that means part of the core has to be solid. Has to be. Now, what they tell about modeling this to get these angles to come out right, it has to go in and then come back out. That basically is modeling that something is different in here too, and that means liquid here from the next slide, but then it must be solid again in the middle. So it tells you you do have a discontinuity in densities, and it's probably not as abrupt as this one is, but there is something else going on there. So that tells you the solid core. Wow! All this put together in this way, yeah. The S waves, larger S wave shadow zone, all the way from 103 degrees to the next side at 103 degrees, no S waves come through. Huge shadow zone. Okay? The core acts like a liquid, not allowing S wave propagation. Only explanation you do. But that the core does have two parts, the liquid outer part, the solid inner part, and you saw that from the shape that, yes?
If we drill into the core, wouldn't that mess something up? Like stroke the,
Well, yeah, it would mess us up. Yeah, if you were able to drill all the way through, no one's got a bit that long, okay? This is 60% of the Earth's mass here. You can't get your way all the way through the mantle. In fact, you can't get very far into the mantle. I don't think any of our bits are sharp enough to do the mantle. It's too, but if you could, yeah, then you would have a vent here for that high pressure molten liquid to come shooting out, you'd have a major volcanic problem. Huh?
It's sort of super volcano or something.
Yeah, it's super volcano, absolutely. Absolutely, yeah. Nah, we don't want to even try it. Okay? But it's an interesting concept, though, isn't it? All right. All this is supported by the combination of what we see with no S waves getting through. There has to be a liquid in the core, around the core, and that the P waves come out at that shape. They come through, but with that shutter zone means there has to be some major discontinuities there, which means it has to be solid in the innermost part. That's the only way they can model it to make it happen. Now, other core evidence, okay? Let's go back to the meteorites again, okay? The iron meteorites are mostly iron and iron nickel alloy, okay? So the stony meteorites, they look a lot like our mantle. The iron nickel meteorites, they're thought that must be what the core is like. Because we don't find anything anywhere that looks like mostly iron and iron nickel alloys with no silicates to speak of or other things. Wow, what would that be? That must be what a core is, okay? Thought to mimic the chemical composition of the core. Whereas the stony meteorites, that's not like anything we find on Earth, so that must be what our mantle is like. And the crust, we know what the crust is like, okay? So that's how the meteorites help us to imagine what the others. And when you do densities and things like that, yeah, it pretty much matches. Earth's magnetic field, the source is some type of turbulent flow within the liquid core. So if you imagine the Earth spinning, which is a crusty exterior, inside that is a huge thick mantle, okay? And then inside that's a liquid. That spinning of the solid, that has to stay together. The liquid can slide past it. And that interface there that things are knocking against each other, that must be a material that conducts electricity. Yeah, it's iron, okay? And the charges must move. That's what creates the magnetic field, okay? Or that's the only model we can get that would make it work. So the meteorite and magnetic field data are consistent with an iron core, and like I said, the iron and iron nickel alloys, no silicates really much in them. That fits. That all the evidence put together, modeled together, this is what comes out with the conclusion. Because we know approximate densities there. So let's now look at a little more detailed structure. Before, all we did was crust, mantle, core, outer core, inner core. Let's take a little more careful look at this. Okay? Now, we already saw a picture that looked something like this. The thick continental crust, made mostly of what? Second? Granite? Yeah. The thinner but denser oceanic crust, basalts. Then we have under the crust, both of these types of crust, we have the mantle. But here we have, this is the more detailed structure. We have the upper mantle and we have the lower mantle. In between those two is a thing we call the asthenosphere. Ew, what is that? The asthenosphere is a thin, now when they say thin, that's relatively thin, not nearly as thick as the mantle or anything else. Maybe about as thick as the crust, but yeah. A thin, hot, elastic. Now what do we mean by elastic? If it, yeah, okay. You got the concept down pretty good. You'd say stretches. When I think of elastic, a rubber band, let's say that, okay? What makes it elastic is it returns to its original shape. That's what it means to elastic. Rubber bands and other elastic things hopefully return to their original shape, okay? and we think of stretching and returning. But most of the time, elasticity also involves compressing and returning. Compressing and returning. Whatever you do to it, stretch it, compress it, whatever, it returns to its original shape. So it's elastic, meaning it bounces back. It comes back to its original shape, but it's a semi-liquid. I don't know exactly what that means. It has solid characteristics, but it also has liquid characteristics, okay? Almost like a liquid, but not quite a solid, a little bit of a liquid layer, and it's somewhere there in the upper part of the mantle. Underneath the upper part of the mantle, the bulk of the mantle is below it, so somewhere in the upper part is the asthenosphere. Now, it's distinguished by a sharp decrease in the seismic wave velocity. Okay, sharp decrease in seismic wave velocity, because it's mantle above, mantle below, it changes its velocity there. Part of that is it's hot, semi-liquid, okay? The solid transmits it fast, dense. The liquid sort of slows it down a little bit. Now, it can't be totally liquid, or the S waves wouldn't travel through it at all. So it has some solid characteristic to it, okay? But it also has a few of that, okay? Now, another term here, that's the asthenosphere, that's this thin band. The lithosphere, litho meaning rock, stone, stuff like that, that's the part above the asthenosphere. That includes some of the mantle, the uppermost part of the mantle, and all the crust, okay? So the lithosphere is a solid layer above the asthenosphere, includes all of the crust, the continental crust, the oceanic crust, the moho, the mohorovic discontinuity, and the upper part of the mantle. All the mantle that's above the asthenosphere and crust on down. Now, it also involves the oceans too, but we're not really worried about those. Okay. Now, this lithosphere is made up of your rigid plates. Okay. This is where your plate tectonics. When they say semi-liquid, it's the asthenosphere here, that's what everything else, this is a strange way to say it, floats on it. Okay, it's allowed to move. See, if it's on solid rock, how can it move? It can't. So we need to have this in here, and we do, and that's what allows the plates to move. The plates are your lithosphere, upper part of the mantle and all your crust. So it's not just the crust, it's the upper part of the mantle as well. And that's the role of the asthenosphere, is to give the substrate for that to float on, to be able to move around as plates. The lower part of the mantle, that's solid. It doesn't move. Okay, it spins, but it doesn't move. Okay. So, yeah, I think we got that knocked, right? Now, here is then the theory of plate tectonics. The individual continents shift positions on the Earth's surface because they're on these plates that float on the asthenosphere. The patterns between the continental shapes can be fit together. Now, y'all wake up? All right. Okay. I think this is the one. Yeah. Have you ever noticed this before? Yeah. Look at the Atlantic Ocean. Notice how Europe sort of fades off in this direction, but North America moves in this direction. And how Greenland sort of fits right in that pattern there. Look at that. And you can almost see, and boy, especially how Africa juts out and the Gulf of Mexico punches in, how South America, especially Brazil here, just pokes right into the part of Africa here. Yeah, look at that. Say again?
Kind of looks like Maine might fit right on top of Spain right
Yeah, okay. What did you say, Wood?
there. I know it's like Maine and the.
Maine, yeah, that Maine would, yeah, maybe either right, yeah, right there. Yeah, it sure does look like that. And maybe Great Britain crushes into there. I don't know, yeah. You can make up and maybe a little bit of that came out of there. Yeah, it's pretty interesting how this looks like it could fit. And that this distance is fairly constant through here. Not exactly, but fairly constant. Now part of this is because we're drawing a globe shape onto a two-dimensional that's going to get expanded at the bottom. But yeah, if you imagine this, look at how closely that would be fitting. Now, individual continent shift, we think patterns between the continents look like they could fit together pretty nicely. Here is the theory, the background of plate tectonics, that at one time we were one huge continent, and that was called one large landmass, Pangea. Pan means a pandemic covers everything. Everybody gets it, okay? Pan America, that used to be an airline, travel all over the world, not just America, but all over the world. Pan, covering everything. Gea basically is almost the same root that we have for geology, geography. That's the Earth, geocentric. So one landmass covering, not covering the Earth, but in the Earth. Now, the first people that looked at this and said, I wonder if the continents have drifted apart. They called that continental drift. They were laughed out of the room. You've got to be crazy. Continents don't move, they're fixed, they're huge. How could they move? And yet now plate tectonics shows us how they could. If we understand that structure, that fine structure of the Earth thing, if it really is like we model it to be, hey, yeah, that may be exact. In fact, we think it is what's happening. Okay? And the people who used to do it, of course, they're all dead by now, that first came up with the idea. They're going, So what is the evidence from the Earth's magnetic field? We hit the others. It seems like these are just so weird an order here. Igneous rock record and the Earth's magnetic field strength and direction are tied together. Now this is one of the strangest things. Thank goodness it's there. It gives us the evidence. But why it's there, I can't think of any much of a good reason to explain it at all. But here's what we've got. Remember earlier I said magnetite and hematite, two different minerals, have exactly the same chemical structure. What's the difference between them? Magnetite, what's the first 6 letters in magnetite? Magnet! Magnetite is magnetic, naturally occurring magnetic iron ore. Hematite is iron ore that's not magnetic. But other than that, they're identical. Same chemical composition, same crystal composition, same everything, except some of the chunks of rock are magnetic and some of them are not. Okay? Now, the magnetite poles are locked into alignment with the Earth's magnetic field when they were crystallized. Now, what does that mean? Let's say we had some seismic activity. This iron ore coming up from the volcanic matter, spilling out, and then if the Earth had a strong magnetic field and the iron ore sat there, that iron ore is going to try to line up with the Earth's magnetic field. Now, you see, this is all assuming you had the physics chapter on magnetism, electricity and magnetism. You haven't had it, so I'll try to explain it to you. Every iron atom, and there's only 3 atoms like this, iron, nickel, and cobalt. Iron and nickel, the 2 that make up most of the core of the Earth, right? There's some cobalt in there, but it's not a whole lot. But those 3, and in your periodic table, they're all right next to each other. there's iron, there's cobalt, and there's nickel. All three in a row there in the transition metals, and those are the only three that their individual atoms are actually little magnets. Every one of them. Because of the spin of the electrons and the structure and stuff, they happen to every one of them be little bitty magnets. Now, most of the time, when, say, the iron, nickel, or cobalt comes out of solution, you have some magnets this way, some this way, some that way, some this way, you have every which way, and they're not magnetic. That would be magnetite. No, I mean, that would be hematite. But, if you have little bundles of these that all, or mostly, they won't all, but mostly line up in the same direction, then you have magnetite. This chemical composition is the same, the crystallography is the same, it's just that these are magnetic, the others are random. They all, each individual atom is a little magnet, but when they cancel each other out, North Pole pointing this way, North Pole pointing that way, but when more of them point in the same direction, you get a naturally occurring magnet. By the way, we call that, the old name for it was lodestone. If you found a piece of iron that was naturally magnetized, that was lodestone. That meant that when it formed, the Earth had a strong magnetic field, and just the way it formed there, they call them domains, mostly pointed in that direction, making it a magnet. Then it hardened and was fixed like that. Okay. That part I understand. That part makes sense. The magnetic poles, magnetite poles, locked into alignment in the Earth's field, with the Earth's field on crystallization. Now, here's the part I can't explain why, but the rock evidence is makes it obvious. The Earth's magnetic field varies in strength and direction over time. Why? I do not know. I cannot imagine. But I do know that lots of things follow periodic motion, periodic activity, which means something may be very strongly polarized now, no polarization in the opposite direction. Put a sine wave there, and I'll buy that. I don't know why it happens, but it's saying that the Earth's magnetic field sometimes is strong, sometimes is weak, sometimes reverses. And that has happened periodically over time. Everything's happened periodically over time. The ice ages, the seasons, everything happens periodically over time. I don't know why it has, but it has. Okay, that's a fact. Now, what they've done is core down through different layers of iron sediments that came out of volcanic activity. And as they core down, they'll find some, well, let's see, I think they have a picture here. Yes. And by the way, the Earth's magnetic field, we spin around the pole, okay? In the northern hemisphere, to point to the North Magnetic Pole, which is in very northern Canada, and around the Hudson Bay, that kind of area up there. For here where we are in Birmingham, right up here, 33 degrees, 23 minutes, 45 seconds, to point toward that pole, we point this way, which is at an angle. It's not north, it's north, downward. So that's why they draw them this way. So you'll have layers of magnetite from the cooling lava that the magnetic field is pointing like this. Now they didn't show it here, I wish they had. I think there's probably other layers that don't have any. But then you'll find a layer that is pointing like this, or several, and then they go back to pointing like that. Now my guess, and I don't know this for a fact, my guess this is a gradual thing. It's not just suddenly they change direction. I bet you it was strong, weaker, weak in the other direction, stronger in the other direction, then weak, and I'm guessing it did like a sine curve. If it didn't, I have no idea of why that would be. But as they've drilled deeper and deeper and deeper, they have found 22 reversals of the Earth's magnetic field over the past 4.5 million years. That's only million years, not billion, million. Not that long, but seems like a long time to us. Okay? Oh my goodness, could it be true?
Yes, it's true.
Oh no. Don't tell me. Let's see. Okay. Anyway, we'll leave it there with that slide. Where will we pick up next time? Thank you so much. We'll start with evidence from the ocean. These will all tie together more. I wish we would have had more time to do it. Okay. You finished the lab? Good. Okay. So evidence from the ocean, that's where we'll begin. Okay, good deal, good class. Well, next time we will, of course, I'm doing this little thing there too. We will start in the classroom and leave immediately to go to Sanford. We'll be at Sanford. I'm guessing we'll get back here 3:15 or so. Maybe 3:30. We'll have maybe another hour of class, continuing chapter 18, and then the last 30 minutes, 4:30 to 5, we'll have the test. Okay. All right, good deal. How's this going? Pace too slow, too fast? Is it
No, I
okay?
like it.
Okay, good.
Yeah, I